yesterday, the first day. So, and I'm sure we will also enjoy the second day. And okay, so just a quick reminder that if you would like to ask questions, please wait at the end of the talk so we don't interrupt the speaker continuously. And also you have the possibility to write questions on the Slack channel. That the link is now on the chat here in Zoom. And also there is a discussion session later after the coffee break. There will be 40 minutes to discuss among us and ask other questions to the speaker if you have. So let's start, and it is a great pleasure to introduce the first speaker. Is Tony Padilla from the University of Nottingham. He's one of the most expert about modified gravity, the cosmological constant problem, screening mechanism. So it is a really great pleasure to leave him the stage for the first talk. So please, Tony.
Okay, thanks, Marco. Can you hear me all right? Everybody hear me fine?
Yeah, we can.
Good. So thanks for the invitation. So I should just warn everybody that if you didn't hear, I had my COVID jab earlier today. So if I say anything that you wildly disagree with or is massively controversial, then I'm just going to put that down to one of the side effects. Okay, so let's just lay that on the table now. So the organizers asked me to talk about sort of the Einstein mechanism, and in particular, sort of UV aspects of it, and the way in which the ultraviolet physics may contaminate the mechanism itself. And this is something that I've kind of been banging on about for maybe sort of 5-6 years now. And really, so what I put together is just a collection of random thoughts that have been developed over that time and some wild speculations, sort of towards the end. So. It was really put together to the purpose of this. So what is the Einstein mechanism? Okay, so we know that people that like to do modified gravity, one of the things that we like to do is perhaps modify gravity at very, very large distances. Now, maybe we've got a good reason for that. Like we want to try to solve the cosmological constant problem in some novel way, or we want to find a new source of dark energy from modified gravity. So what that means is typically that we're doing something quite radical to general relativity at very, very large distances. It corresponds to something like an order 1 change in the theory that's apparent on large distances. And why does that happen? Well, typically you have to introduce some new ingredients, some new degrees of freedom into the theory.
Sorry, Tony. Sorry to interrupt you. Are you trying to move slide? Are you changing slides? Or
no, I'm not moving slides. I'm just rambling. Okay, so typically what you do when you do that is you introduce some new degrees of freedom into your theory, and that's what's giving you the modification. But then you realize that when you start thinking about physics on solar system scales, when you start thinking about gravity in the solar system, you know that matches general relativity very, very accurately. So whatever new physics you introduce to do your magic at large distances had better be suppressed by the time you look at the physics in the solar system. And that means whatever new degrees of freedom you introduce need to somehow go away. And this really is the whole sort of game that you play when you think about screening mechanisms. You need a screening mechanism in this language is just something that's going to suppress those extra degrees of freedom within the solar system, whilst allowing them to do their magic at larger distances. Now, there are various screening mechanisms. We'll probably hear about others today. Things like the chameleon mechanism, the symmetron mechanism, and of course, the Einstein mechanism. Now, what sets the chameleon mechanism and the symmetron mechanism, they kind of work by effectively changing the mass of in particular the chameleon mechanism, by changing the mass of the new degrees of freedom. So those new degrees of freedom get heavy in some sort of dense environment like the solar system. And that shuts down the corresponding force. The Einstein mechanism works slightly differently. Typically, it relies on the presence of higher derivative operators, so that when you're in an environment like close to a heavy source, it turns out that you get this kind of Z factor, what's called a Z factor. You get the effective coupling of your degrees of freedom to matter gets very much weakened in that environment close to the source. And as I said, this Einstein mechanism, which typically originated by thinking about massive gravity, but is now more general than that, it really relies on the presence of sort of higher derivative interactions. And that in itself brings some worries. For the Weinstein mechanism to work, these derivative interactions have to be important, at least in the classical theory. But as you know well, the minute you sort of have these sort of high derivative interactions appearing in your theory, that also implies at the quantum level that there's a breakdown in perturbative unitarity. And so it asks the question, if these terms are so important to sort of making the mechanism work, and I know that there also corresponds to some sort of sickness or misunderstanding in the quantum theory, then I have to worry about how to fix that in the quantum theory and what impact that might have on the classical theory. So one of the things I'm going to emphasize is that whatever new physics that comes in to cure the quantum theory, that sort of to preserve unitarity in the quantum theory, may have some far-reaching implications in terms of the sort of the success of the Weinstein mechanism. So whatever new degrees of freedom kick in, or whatever new physics appears to sort of cure the problems with the quantum theory, could actually propagate out to macroscopic distances and create a problem for the Weinstein mechanism. So I'm going to start. Oh, can I change slides? Oh yeah, there it is. Okay, so this is just a rough outline. I'm going to sort of begin by giving a sort of baby-like introduction to what the Weinstein mechanism is, for those that haven't really come across it before. And then I'll emphasize some of the challenges that we immediately see from the ultraviolet sector of the theory. And those that have worked on sort of positivity constraints will know these well. I'll also talk about the possibility of sort of getting around these constraints with infrared deformations. That seems to be an avenue that's closed off recently. But even if it hadn't been, I think it would have created problems for the Weinstein mechanism. And I'll conclude with some sort of random rambling thoughts at the end. So, as I said, this is work that I've been doing for sort of several years now, and thinking about for several years. Here are a list of all the people I've worked with on these topics. Many people over a long time. Okay, so let's go back to the early 70s and think about massive gravity. And the people that are far more expert on massive gravity than me here, but let me just give you some of the basics. So what happens when we give the graviton a mass? Well, the way you do that, at least the leading order, is to introduce the Pauli-Fierce-Matz term, which you see there. And what this does is this ensures this is the right combination of terms that guarantees that you actually have the right number of degrees of freedom in, for example, 4 dimensions. So in 4 dimensions, a spin-2 particle with mass is known to have 5 degrees of freedom, in contrast to a spin-2 particle without mass, which would have 2. And this combination of terms in the mass term actually gives you the right number of degrees of freedom. So you might look at that and say, well, okay, how do I recover general relativity from this? Well, I can just send the mass to 0, right? But that doesn't quite work. It turned out, and this is a really important feature, that the m goes to 0 limit doesn't actually correspond to general relativity. This is known as the VDVZ discontinuity. Now, sort of on a sort of technical level, what happens is that you look at the structure of the propagator of the massive gravity theory, and you take the mass to 0, and you don't recover the propagator of general relativity. And there's a very good reason for why that happens. And it really comes from that degree of freedom count. As I said, a massive graviton has 5 degrees of freedom in 4 dimensions, whereas a massless one has 2. So it doesn't matter how light you make the graviton, if it's still small, if it's non-zero mass, albeit infinitesimally small, it'll still carry 5 degrees of freedom. And actually what happens is you take the limit as m goes to 0, is it's not that those extra 3 degrees of freedom decouple, in fact, some of them become strongly coupled. And that's what causes the discontinuity. And already there, we're seeing perhaps this issue of strong coupling, which is going to be a theme throughout what I'm going to discuss. So this was kind of thought to be a bit of a disaster for the phenomenological success of massive gravity. But then along came Weinstein and said, well, hang on a second, let's not be so fast. We know that GR is already a nonlinear theory. Okay. What about massive gravity? In principle, there could be higher order interactions. They are there present in the theory. You can write them down. And what these do is that they can, if you take a sort of heavy source, like the sun, for example, some heavy source of mass m, and what you can show is that the higher order interactions can help suppress those troublesome extra modes sort of close to the source. So below some critical scale, which is known as the Weinstein radius. So close to the source, the extra degrees of freedom are suppressed by these interaction terms. Now, this you see here the formula for the Weinstein radius in terms of the mass of the source. It also contains this scale lambda 5, which is the scale at which the quantum fluctuations on the vacuum will become strongly coupled, or which perturbative unitarity breaks down. And again, that's going to be an important theme. And the success of the Weinstein mechanism is directly related to the presence of that strong coupling scale. Now, just to put some numbers into the story here, I'm going to have to move the picture because you guys are in the way of what I'm looking at. So if we take a sort of Hubble mass graviton, and for the sun, we have a Schwarzschild radius of about 3 kilometers. The corresponding Weinstein radius would be about 10 to the 18 kilometers, which is larger than the size of the solar system. So what this tells you is that inside the solar system, the higher order interactions are successfully suppressing those extra modes. And so you're able to recover general relativity. Okay. So this was Weinstein's point. Now, just as a word of warning, I mentioned this strong coupling scale, which turns out to be present in the theory, which is the scale at which the quantum fluctuations become strongly coupled. And in this particular case, that turns out to correspond to a distance scale of about 10 to the 11 kilometers, which is obviously a huge distance scale for quantum effects to break down, essentially, to become important, to basically have a violation of perturbative unitarity. So that's already a concern. Now, of course, it turns out you can improve the situation a little bit. You can be careful about the choice of interactions, and you can actually lower the strong coupling scale a little bit, and in a way that still gives you the kind of dynamics you want. So, just again to put in the numbers, with this sort of some clever choice in the interactions, you can, again, for the sun and for a Hubble mass graviton, you would have a Weinstein radius which was still larger than the solar system. But now the strong coupling scale now becomes this lambda 3 scale. It comes down a bit, and it corresponds to a distance scale of about 1,000 kilometers. So there you have a situation where quantum effects are essentially, quantum theory is becoming strongly coupled at around 1,000 kilometer scale. So perturbative unitarity is breaking down. Okay, so you're really starting to lose some predictivity in your theory. Okay, so let me sort of just illustrate how all of this works with a toy model. Okay, so this is a very simple toy model, and it's going to sort of show us some of the key features. So here we have general relativity plus a scalar. Now, if you ignore that sort of interaction term, the term with lambda in the middle there, the d phi to the 4th over lambda to the 4th, ignore that term. If we didn't have that, this would just be like a Brans-Dicke type theory, where the extra scalar is coupling to the trace of the energy momentum tensor with the strength sort of comparable to gravity. Now, but we're adding this interaction term, okay, this 1 over lambda to the 4th term. This lambda scale is the scale at which that interaction term becomes strongly coupled, and we're going to take that to be well below the Planck scale. And for now, I'm going to allow this interaction term to have either sign. So I want to explore some of its effects, at least in the vicinity of a heavy object. Okay. So let's look at its scalar profile around say, the sun. You can write down the field equations. And what you find is that very, very far away from the source, the scalar profile basically just does what you expect. Okay. You can ignore the interaction term, and you see that the scalar profile is roughly comparable with the Newtonian force. So this corresponds to an order 1, a theory with an order 1 modification of gravity at large distances. Now, this one doesn't do anything particularly interesting, but it illustrates the point that you've got a large scale modification, you've got a large modification of gravity at large distances. But what happens here is, as you move closer to the source, okay, eventually there's a critical radius, which is given at the bottom here. This is another version of a Weinstein radius. And inside that radius, the cubic term here, so this cubic term in the field equation or the interaction term in the Lagrangian, that becomes important. That starts to dominate, and it changes the behavior. Okay, and what you find is that the force associated with the with this new scalar now, rather than dropping like 1 over r squared, it drops like 1 over r to the 2/3. Okay, so this is now basically this is suppressed with respect to the standard Newtonian force. Okay, and so this is screening in action. Now, this procedure only works for one particular choice of the sign of the interaction here, and this is going to be important. I need to take this interaction term to be negative to allow me to actually continue the solution from the sort of large distances right towards the source. If I take the other side, if I take sigma to be positive, then basically my solution breaks down roughly around the Weinstein radius, and I can't continue the solution in, and there is no Weinstein effect. But for sigma negative, I can do it. I can take the solution all the way in, and I get this screening close to the source. Okay, so this works really nice. And what I want to do now is because I want to make the connection with quantum theory. I want to sort of describe this process of the linearized approximation breaking down in this kind of a kind of Feynman diagram language, but even at a level of classical theory. So this is sort of illustrated by this picture here. So what we've got is the black dots correspond to insertions of the source. And when you're doing you can imagine through perturbation theory at large distances, to leading order, you just have the source sort of coupled to the, you sort of, well, you can see it here. You use the propagator as the Green's function to sort of calculate what the scalar is, and then you can order by order include the contribution coming from the interactions. And this is sort of shown diagrammatically here. This kind of expansion will break down at some particular radius, okay, at some particular scale, and it breaks down, no surprise, at the Weinstein radius. So that's basically telling you when this leading order behavior sort of starts to fail, and you have to go to something truly nonlinear. Okay, but now I want to compare that with what happens in quantum theory. So in quantum theory, you talk about propagators and you talk about loop corrections. And you see something very similar. So you calculate suppose you want to calculate the correction to the scalar propagator here, then obviously because you have this 5 to the 4th interaction, you can consider a loop correction like this. And this expansion, this perturbative expansion that you're doing, is an expansion in basically energy over lambda to the 4th power. Okay, where E is some cutoff scale in your theory. Okay, so this expansion that we're doing here is really deeply connected to the classical expansion we did in the previous page. It's something that the classical expansion broke down at the Weinstein radius. This expansion breaks down at the scale lambda, which is the scale of strong coupling, and this is where perturbative unitarity breaks down. And those two breakdowns are absolutely related to one another. And it's just really an artifact of doing perturbation theory. Okay, so you can't have one without the other. So the connection between Weinstein screening, okay, and some breakdown of classical perturbation theory at some very large macroscopic scale is intimately related to the breakdown of perturbative unitarity, also at a sort of much lower energy scale than you would like. Now, this kind of point's been emphasized maybe a good decade ago by Diwali, but it's a really important point to make because it shows that the potential sort of lack of knowledge of what's really going on in the quantum theory beyond a certain scale is intimately related to your desire to actually have a Weinstein mechanism. Okay, so typically when you have a breakdown in perturbative unitarity in the quantum theory, what you would do is you would say, right, I need new physics. And we know that we've done this many times before. For example, WW scattering sort of becomes non-unitary, and then you say, right, I need to introduce the Higgs. And the Higgs unitarizes everything. And that's the standard Wilsonian picture of how you sort of allow a theory to sort of build into the ultraviolet. Now, let's imagine for a moment this is how things are done here. Okay, And we'll see maybe later that maybe that's not the case, but let's imagine for a moment that it is. So you've got your 4-point interaction here. We're going to try and smooth it out with some new physics. Okay, so we integrate in this new field, which is the red propagator there. And this is going to be some heavy field. Okay, now its mass should be slightly below the scale of strong coupling, so that this new physics becomes important before the theory starts to violate unitarity. Okay, so why is this a good thing? Well, now we can start to look at this propagator and look at the breakdown of the quantum theory, and we see, well, this isn't the right thing to think about anymore, all the way up to the scale lambda. We know that this 4-point interaction that appears in this here is not really there anymore, that it's really should be replaced by that, because we've got this heavy field now, which is playing part of the game. Okay, so this allows you to push the theory to higher energies in a consistent way. Now, this is all fine, but now we have to ask, what is it going to do to the class? What is introducing this new degree of freedom? Is it going to affect our classical story? And it seems clear that it is. If we go back to our classical picture of how we were doing linearized perturbation theory about a heavy source, then we had this picture where we sort of built up the effect of the interactions order by order. But now we're saying that the interactions, we're smoothing them out with this new heavy field. So rather than looking at this picture here, we should really look at that picture. And this suggests that there could be a macroscopic effect coming from the new physics, sort of, that could potentially contaminate the Weinstein mechanism. It may destroy it, it may not destroy it. The point is, we don't know. It may do something. Okay, so if there is new physics there, it seems, and you know, we can debate whether there is or not. If there is new physics there, then it absolutely is important to know what it is, because its effect could, in principle, propagate out to large distances and affect your predictions for what you would expect to see inside the Weinstein radius at some scale. So that's just to make that point. So I want to now draw an analogy with general relativity, something that happens in general relativity. So you can think about general relativity also in a very similar way, and you can make an analogy between the Weinstein radius and the Schwarzschild radius in general relativity. So way back in the early 70s, Duff showed how you could recover the Schwarzschild solution, basically just doing linearized perturbation theory and sort of extensions thereof. So this is a very similar picture, where here and now these solid lines are gravitons, the circles are insertions of a heavy source, and you order by order build up the response, the correction to the solution coming from the heavy source in this interacting theory, which is general relativity. When you ask, what is this an expansion in? It turns out it's an expansion in the Schwarzschild radius of that source. And of course, because you have diffeomorphism invariance, you can resum this and you end up with a Schwarzschild solution. But strictly speaking, if you just look at it as a perturbative expansion, it will break down at the Schwarzschild radius. Now, that's all fine. We know that breakdown of sort of the Schwarzschild radius is actually connected to sort of violation of unitarity in GR at the Planck scale. So we're seeing a similar picture there. Okay, so those two things are connected in the same way they were connected to the Weinstein story. And you know that you expect new physics to come in, some new physics, most likely stringy physics, to come in just below the Planck scale, that there's some new scale, the string scale, which is sitting below the Planck scale, and that helps sort of unitarize the theory. Okay, so if such a thing happens, what effect could it have? Well, let's ask. Okay, so one thing we might say is let's try to include some sort of stringy corrections. Let's look at d-dimensional general relativity and include a kind of plausible stringy correction that we can at least calculate with. And one such thing might be a sort of Gauss-Bonnet term, which I've written down here. And this Gauss-Bonnet term, which is squaring the curvature, is weighted by the string length scale. Okay, and what you see is that we can ask now, what are the black hole solutions associated with this sort of larger theory, with this stringy correction coming from UV physics? And you can calculate them and you can find them. And what you find is that you just get some potential, which is all fine. but this is not exactly the same as the Schwarzschild potential. It's slightly different. So it seems that the new physics is giving us a correction. Now, the question is, at what scale does that correction become important? Is it going to be very close to the Planck scale or the string scale, or is it potentially at a macroscopically much larger distance? Well, let's have a look. So what you can do is you can do an expansion for large R, and you can see that it's a leading order. You will get something which resembles Schwarzschild in d dimensions. And there is a correction which kicks in at some critical scale, which I've called R star here. So that's the scale at which the corrections to your theory, which have come from stringy physics in principle, are important. And what you find is that scale is, again, it's not necessarily close to the string length scale. It's a much larger scale. It's not necessarily all the way out to the Schwarzschild radius, but it's a macroscopic scale nevertheless. And so I feel this is a lesson that we need to bear in mind when we're thinking about the physics of Weissenstein screening, that there could be sort of ultraviolet physics lurking beneath, which could propagate its effect out to an unexpectedly large distance. Okay. So just to come back to our toy model now and Weissenstein screening, and something I want to emphasize is, so we're going to worry now about what the UV physics might be. And for this kind of theory, you might try to guess that the UV physics just comes from a Higgs-like completion. Okay. Unfortunately, that doesn't quite work. So you can get an action which looks quite a lot like this from sort of a spontaneous symmetry breaking and the Higgs mechanism, where the scalar phi would correspond to sort of the Goldstone boson. But unfortunately, the sign that you get for the interaction is positive. And we've just realized that to get Weissenstein screening in our toy model, the sign that we need has to be negative. So there's a mismatch there. Okay. Our natural way to UV complete the theory actually gives us the opposite sign to the one we want for Weissenstein screening. So that's kind of problematic. And that betrays a bit of a problem that we're finding with even being able to sort of even try and UV complete these theories. And this leads us to the story of positivity. So there are people, I'm sure, in the audience who are far more expert than me on this, but let me give a flavor at least of what this story is. So back in 2006, Adams and friends sort of revisited a lot of the old sort of 1960s S matrix theory stuff involving scattering amplitudes and S matrix theory. So in the case of a scalar, let's suppose we consider 2-to-2 scattering of a massive scalar particle. We express it in terms of the usual Mandelstam variables, S, T, and U. Now, one thing you can do is you can go to the forward limit and you can ask how the amplitude behaves. And generically, it will go like, because this is a massless field, this is typically going to go like some S squared over some scale to the 4th power. But you can say a bit more than this, based on requiring that the fact that even though we're talking about low energy effective field theory here, that it has a UV completion that is consistent with causality, unitarity, and locality. If that is true, you need that the coefficient of that term be strictly positive. Okay, now if we start to think about our toy model, for example, that we wrote down in the previous slides, well, what sign does that leading order term have for our toy model? Well, we know it turns out it has the same sign as our sigma, and this makes sense. We knew that when sigma was positive, which was when we couldn't do Weissenstein screening, we were able to UV complete the theory. Okay, so that we should hope that we get the right sign there, and indeed you get a positive sign for the amplitude. In contrast, the case where we could do Weissenstein screening but had no UV completion, then the sign is negative, and that agrees with the conclusion here. For so-called Galileons, for example, the sign is actually vanishing. It's actually a vanishing one. So that again isn't compatible. Okay, so one way you might try to think about getting around this is to think about deforming the theory in the infrared a little bit. So one thing you might hope to do is to say, right, these issues with the positivity leading to constraints on UV completion, they're sort of really looking at the infrared sector of the scattering amplitude. Maybe I can just deform the infrared a little bit, but then have some higher order, but then the kind of behavior that I want emerge at some higher scale. Okay, so the idea would be to sort of have almost some approximate version of the screening, but with some infrared deformation that allows you to skate around the positivity constraints. So for example, suppose we took a Galilean theory. So this here is the Galilean theory, which has some nice Galilean symmetry, which I won't go into now. But this is a theory which, if you just write it down as is, will give you screening. Okay, and we see it here. At large distances, the scalar competes with the Newtonian force. There's some critical radius, which is the Weinstein radius. And inside that radius, the scalar force is suppressed. Okay, so this is a theory which exhibits screening. Okay, so what you might want to do to this is deform it. So the Galileans as given do not satisfy the positivity constraints. Okay, so they can't be UV completed as they are, in a standard way at least. So what you might say is, okay, I'm going to deform it in the infrared. For example, I could add one of my d phi to the fourth terms, but with the sign that doesn't give me screening, but which does give me UV completions. Okay, so I could deform, but right, so I add this term. So now I add it with a positive sign, so that now I hope I can get past my positivity constraints. But the trouble is I can't make that term too big. Now, one obvious reason why I can't make it too big, if I make it too big, it will potentially spoil the Weinstein screening. Okay, so there's a bit of give and take there. So one of the things that we thought about was, well, how big can it be? So Bellatini et al., this was about 3 years ago now, were able to define an improved analyticity bound on these kinds of deformations. And what they were able to show is, well, they were basically doing sort of effective field theories, and they were able to say, right, suppose you work with effective field theory, when you talk about predictions, you do it to some sort of level of accuracy based on the cutoff, how far you are from the cutoff, and so on and so forth. And what they were able to do was, you say, right, you make some statement. I'm going to be within, say, 1% of the cutoff. I'm going to be within sort of 10% of the cutoff. What can I say about the kinds of interactions that I'm adding here? What can I say about the size of them? And they were able to derive a bound. And the consequence of this bound is that, again, that basically this coupling G, the size of this coefficient, it needed to be bigger than 10 to the minus 13. So, okay, that doesn't seem like a very big number. So that sounds like it's probably not going to be enough to spoil the Weinstein mechanism. Remember, it's positive. So if it were large, it would spoil the Weinstein mechanism. It would destroy, it would dominate over the Galilean, and we'd have a problem. But that's quite a small number, is it? But is it small enough? So what you can do is you can go ahead and you can ask, how big is the number allowed to be before it does destroy, before it does sort of swamp the Galilean and start spoiling Weinstein screening? And you get a bound on that. It's not too difficult to calculate. And it turns out that bound is actually much stronger than expected. So you cannot, it actually turns out that in order to not spoil screening, G has to be much smaller than 10 to the minus 13. Okay, so basically, at least for the sun. So it turns out that this deformation just isn't going to work for you. Okay, and actually recently, very recently, we've even sort of Bellatini and his collaborators, and Andrew Tolley and his collaborators have actually been able to make stronger statements still, now suggesting that this G's, if you're going to do these kind of deformations, that they're going to be after order 1. And there's absolutely no way you can have a sort of an approximate regime where the amplitudes are doing kind of interesting things which might be compatible with Einstein screening. So that's a suggestion. That's actually a suggestion that things like this just aren't going to work. Okay, I want to report.
Sorry, Tony, just a second. You have 5 minutes left.
That's fine. Yeah, no problem. So I want to report on very quickly on one thing that we looked at recently about massive Galileans, which again are a theory. It's a truncation of a low energy theory, which again has exhibits Weinstein screening. Now, I won't go into the details, but this is like a sort of has a high derivative interaction. It has a mass. There is, again, suppression of the scalar force within some critical radius. Okay, but the nice thing about this theory is I can UV complete it. Okay, I can UV complete it by integrating in a heavy field, and this was at least for one class of models, was shown by de Rham and friends. So I actually have a UV completion for this theory. Now, you might not like the underlying sort of low energy effective theory because it contains these sort of box pi operators, which seem to contain high derivatives. But either way, it's clear that this has. But you know, one of the things we want to emphasize is that this is an operator which does require new physics to kick in before the scale lambda. And I don't think really doesn't feel like the other. This seems to be true sort of universally throughout any theory with Weinstein screening. Anyway, so we had a UV completion for this theory, and I sort of low on time. I won't go into the details. But safe to say it can be UV completed in a case for n equals 2 and 3. For the higher n, you can at least raise the strong coupling scale in a natural way. But the thing that we looked at was we started looking at screening in both the low energy theories and in the UV completed theory. So the effect of screening in the low energy theories is shown here with the dotted line. So this is taking the sort of the upper action, the truncated low energy effective action, which is essentially what people do whenever they're playing around with the Weinstein mechanism for the various values of n. And what we see is here, we're comparing the scalar force, it's all had to be done numerically, we're comparing the scalar force to the Newtonian force. And what you see is you really do see screening happening, sort of as you get closer and closer to the source. The ratio of the scalar force to the Newtonian force is dropping, and that's screening. However, when we did this with all the same initial conditions, when we looked at what happened for the in the UV theory, we found that the screening was completely destroyed, and there was no screening at all. So this is again another example of where the UV physics comes, even though you think it's happening at a sort of hierarchically different scale, actually comes in and bites you. Okay, so very, very briefly now, I'm going to mention sort of classicalization, which is the alternative to UV completion that you have here. And basically, so I don't want to go I haven't really got much time to talk too much about it, but the idea is kind of like, you know, when you think about sort of graviton scattering, at very, very high energies, it's not dominated by 2-to-2 scattering of gravitons. It's actually what you expect to happen is the gravitons are going to, 2 gravitons will come in, they'll form a black hole, which will then decay into low energy quanta. It's been suggested, and it's quite possibly true, that this is how you UV complete some of these theories of Weinstein screening. Again, you have 2-to-2 scattering, but that's suppressed at energies sort of beyond the lambda scale, the strong coupling scale. And actually what happens is you form this object called a classiclon, which is kind of just this sort of condensate that's associated with it, which has a size roughly of the Weinstein scale. And that will then decay into low energy quanta. So this is how people often claim that this is how things should be UV completed. What I want to say is that if that's true, then we should potentially be looking for it at the LHC. And the reason is that LHC protons could potentially produce classiclons, which we should be looking for the signatures for. Just to throw in some numbers, very rough calculation, what you find is for typical numbers that you have, for example, in sort of Galilean type theories, the LHC protons will form classiclons of around 10 nanometers. That's 1 billion times larger than its constant wavelength. It suggests you'll have enhanced scattering cross sections. It suggests there'll be missing energy through classiclon decay into these low energy quanta. So if we're serious about these being the UV completions of our theories that do nice things for us in modified gravity, then I think we start having to think about how they are constrained by LHC experiments. So one final thought, just to wrap up, just to really emphasize the point that we cannot ignore the effect of the UV when we're thinking about Weinstein screening. Take a black hole, a heavy classical black hole, much larger than the Planck scale. If it's coupled to this scalar, which has some screening effect, then there'll also be another characteristic scale associated with that, which is its Weinstein radius. Now let this guy decay to give off Hawking radiation. It's going to shrink, and eventually it'll become a quantum black hole, whose size is roughly the size of the Planck scale. Such a black hole would have a corresponding Weinstein radius of around sort of inverse lambda, inverse the strong coupling scale. And it seems implausible to suggest there isn't going to be new physics kick in at that scale that's going to be important. So it really behooves us to sort of really worry about what the new physics, the physics of the scale beyond strong coupling is in the case of Weinstein screening. I'm going to finish with a conjecture, a swampland conjecture, just for a bit of fun, really. So many of you would have seen this on on April Fool's Day from Will Kinney on the archive. So I'm going to sort of sort of acknowledge that and make a swampland conjecture to finish off my talk. And that's that any lower G effective theory of a scalar field coupled to gravity that has Weinstein theory cannot be obtained from a consistent quantum theory of gravity. It's certainly true. It seems to be, I wouldn't say certainly true, but the evidence there seems to be pointing that you can't get it from sort of anything with a Wilsonian UV completion. But I think it's even, I'm going to stick my neck out and say something even stronger, that it cannot be even coupled to a consistent quantum theory of gravity. And yeah, I'll leave it there. Thank you.
So thanks a lot, Tony. That's a quite strong statement, but yeah, it was a great talk. So we have time for just one question that there is a raised hand, and then we leave the other question for the discussion session that is right at the end of the next talk. So a question from Chi-Yi Cheng. I hope I pronounced it well.
Thank you for the talk. So my question is about what if we relax the assumption of locality? So if, for example, if we include some kinds of entire function of box, and in principle we can have infinite higher derivative then, and also it is possibly to be UV complete as well.
So certainly the notion of classicalization sort of is sort of relaxing that condition of locality in the usual way. So yeah, I think that's definitely something you can explore. I think so. So the thing I want to emphasize is that it's not enough just to say, just to sort of put your head in the sand and pretend that the UV doesn't matter. Okay. What I've tried to present is the evidence that if the UV is, the UV can matter. Okay. And even though you might think it's something that's only going to become important at the scale lambda or some scale around there, actually that can propagate to macroscopic scales. Now, the examples I've given where that happens, for example, the case of the massive Galileon, where it had a standard Wilsonian UV completion. Or I think the other example that I think is important here is the case of the Gauss-Bonnet connection to GR, where you see a similar effect pushed out to much larger scales. I think it behooves us to figure out what is the new physics beyond the scale lambda and what effects it could have. Okay, and I think it's no more can we just hold our head in the sand. If, for example, classicalization is the correct way to UV complete these theories, which it may well be, in fact probably is, then I think we have to start asking real questions about classicalization in other contexts. And I think one of those, for example, would be what effect could it have on LHC experiments? Okay, so and that should now factor into how we constrain our modified gravity theories.
Okay, thank you.
So thanks again, Tony, and please let's leave the question for the discussion session. Now we need to go on with the next speaker. And also there is a Slack channel, so if you have a personal question for Tony, you can contact him on the Slack or just write on the day of today for asking question. And let's now start with the second speaker, Kazuya. Kazuya, are you there?
Yeah.
Okay. So it is a great pleasure to introduce the second speaker, Kazuya Koyama, that is professor in Portsmouth at the Institute of Cosmology and Gravitation, and he's going to talk about dark energy and gravitational waves.
Can you see the slide?
Yes, we can.
Okay, so thanks for the organizers for inviting me here. So I was asked to talk about effect of gravitational wave constraint on screening. So I will talk about the connection between dark energy and gravitational waves. So of course, dark energy is related to the accelerated expansion of the universe. So its energy scale is determined by horizon scale, Hubble scale today. So in terms of energy scale, it's like 10 to minus 42 gigaelectron volt. So in terms of length scale, it's 10 to 23 kilometer. On the other hand, we detected gravitational waves by LIGO. So its frequency is like 10 to 100 hertz. So in terms of wavelengths, it's like 10 to 3 to 10 to 4 kilometer. And in terms of the momentum, it has the energy of 10 to minus 22 to 10 to minus 23 gigaelectron volt. So there's like 20 orders magnitude difference in the energy scale. So the question is why these two very different energy scale physics is related. So that's the question. And to see this, I will use the scalar tensor series as an example. And for simplicity, I will consider an action given by this. So we have a scalar field, and it contains first derivative of the scalar field, as well as the second derivative of the scalar field. And this is needed for screening, as Tony explained. So, and then I stick to the Lagrangians, which contains only quadratic of the second derivatives. And so X is just a product of the first derivative, so the kinetic term. And then you can write down 5 possible terms containing quadratic of the second derivatives. And you have 5 functions of phi and x. So these are the arbitrary functions you can have. Then I add this gravitational action. So with this, again, another free function of g of phi and x. So we have 6 free functions to start with. So now we need to impose theoretical consistency. So this is a scalar tensor theory. So 2 for tensor, 1 for scalar. So we want to make sure that we have 3 degrees of freedom in vacuum to avoid the Ostrogorski ghost coming from higher derivatives. So the Hodensky theory we heard yesterday, this ensures this by requiring that the equation of motion is second order. So this requirement gives these conditions, and eventually we end up with just one free function g, and the Lagrangian is simplified to this. However, it was shown by this pioneering paper that in fact, you can have higher order derivatives in the equation of motion if you have a degeneracy condition to remove this ghost mode. And by imposing these conditions, basically you can have 3 free functions in this Lagrangian, and the other 2 functions are determined by this degeneracy condition. So in this extended theory, which still propagates 3 degrees of freedom, you have 3 free functions of phi and x. And you can understand this using this Bekenstein's idea of 2 geometries. So basically, you can come up with an additional metric in addition to the metric you have to describe spacetime. You can construct this additional metric using the conformal transformation and this formal transformation. And in fact, you can show that a subclass of DOST I described is indeed just a transformation of Hodensky using this conformal and this formal transformation. And this explains why we have 2 more free functions in this DOST theory. But of course, I mean, this is just a change of variable. So in the vacuum, the theory is equivalent. But what we do is that after the definition of a metric, 2 related theories are minimally coupled to matter. So then these 2 theories become distinct. So this is the kind of way of generating new theories, and this can be applied to other theories as a side remark. For example, massive gravity can be thought as a theory with 4 scalars, and then you can construct basically a new metric like conformal and disformal transformation to generate new theories. So this is the way of generating new theories using this transformation. So coming back to scalar tensor examples, basically you have these 2 additional free functions. Now you have 3 free functions. So now we apply this to dark energy. So we want to use this to explain the accelerated expansion of the universe. And you're going to find theories. Basically, you need to specify these functions. And you don't want to have cosmological constant nor potential. So we assume that these are the function of x only. Then you can find a solution that the time derivative of scalar fields times Hubble constant is constant in the matter-dominated universe. And this is a tracker solution. So no matter what initial conditions you have, the solution approaches to this. And later this transit to the de Sitter solution with constant h. So this is a Hubble function. This is time. So you have a matter-dominated universe, and then you have accelerated expansion of the universe. But then now you need to ensure that this describes our universe. So this Hubble constant at late times needs to be the Hubble constant today. In this way, we introduce this energy scale. So this is the same lambda 3 Tony had. So basically lambda 3 is given by h naught squared times m Planck. This is a requirement that this theory describes dark energy. And it's very important to emphasize that anything I will say only applies to theories related to dark energy, because I will introduce this energy scale in the theory. So now let's come to the gravitational wave constraint. So the first constraint that will play an important role is the Haussteller binary constraint. We heard about this yesterday. So this is the orbital decay due to the gravitational waves. And in fact, we heard that we have a much stronger constraint now. But for now, let's use this Haussteller binary constraint. And the other constraint, again, we already heard about is the constraint on the speed of gravitational waves. So we observed the time delay between gravitational waves and gamma ray burst from merging neutron stars at the distance of like 40 megaparsec. And this gives the constraint on the difference between gravitational wave speed and the speed of light. And we get a very strong constraint. So just to mention that indeed we have an additional constraint. And so this is coming from the gravitational Cherenkov radiation. So if the gravitational wave speed is smaller than speed of light, the cosmic rays will decay into gravitational waves. So we have a very similar lower bound from this constraint. So now let's impose this constraint. So we want to impose that at least within 40 megaparsec around Earth, the gravitational wave speed is the same as speed of light. And the easiest thing is to impose this condition in a hard way. And then looking at this gravitational wave's speed, you notice that this A1 term, so this is the product of the second covariant derivative of the scalar field, contains the contribution of the kinetic term of the gravitational waves. So this changes the speed of gravitational waves. So if we want to impose this condition exactly, you have to impose this condition, so A1 vanishing. And then the rest of the functions are determined by the degeneracy condition. And one thing you notice that this already excludes the Fordensky theory with g function of x, because A1 is related to this function. So if you set A1 to 0, then you cannot have x dependence in the Fordensky theory. So now you reduce your free function from 3 to 2 by imposing this condition. And again, you can understand this easily by using this disformal transformation argument. So you can go to the Fordensky theory by doing this disformal transformation. And this conformal transformation does not change the light cone. So now you couple matter to this G tilde, but this conformal transformation does not change the light cone of the matter. But this disformal transformation does. So basically, this means that you can tune this D function to make sure that the speed of matter is the same as speed of gravitational waves. But in this way, you fixed this freedom. So you only have one freedom left in addition to Fordensky. So that's the reason why we have now two free functions in the theory. So this is one result of imposing the gravitational wave constraint coming from the gravitational wave speed. So now we come to this solar system test. So of course, we have to satisfy the solar system constraint. So in the solar system, we basically parameterize our metric. And this is the Newtonian potential. This is the curvature elevations. And gamma is a parameterized post-Newtonian parameter. and gamma is strongly constrained, so like 10 to minus 5, as well as this nonlinearity in the potential. And another important constraint we can get is using the mirror on the moon, and we can measure the distance to the moon very accurately. So any deviation of this gravitational potential from GR projection is strongly constrained. And another constraint is the time evolution of Newton constant, and this is now constrained like this. So all of these constraints need to be satisfied in any modified gravity models. So here comes the Einstein mechanism. So I will use yet another different model which has Einstein mechanism to demonstrate how this happens. So in this model, I consider a 5-dimensional model, so known as DGP, brain world model. So you have a 5-dimensional space-time, and you have a 4-dimensional brain, so you're living on this brain, and you have the usual Einstein gravity on the brain. Now you have 2 Newton constants, so 5-dimensional Newton constant and 4-dimensional Newton constant. So this crossover scale is the ratio between the two. And you notice that in this case, in fact, the gravity becomes 5D if you consider length scales larger than this crossover scale. So RC has the dimension of length. And this can be easily seen by looking at the Friedmann equation. So this is the expansion of the universe on this brain. So this part is just coming from usual 4D Einstein gravity. But this contribution is coming from 5D gravity, and it scales like linear in h. So this term is important at late times at low energies. And even if the matter disappears, you can have a solution where h goes to constant. So this is the accelerated expansion of the universe. But again, I have to emphasize that now we introduce this energy scale, horizon scale today, to use this theory as the dark energy theory. Just to mention that this theory doesn't work, so this solution is indeed basically having the ghost, so it's an unstable solution. But for the sake of introducing the Einstein mechanism, this is the interesting theory to look at. But the important thing here is just that this parameter needs to be the horizon scale today to be a dark energy model. Now you can look at the behavior of gravity in the small scales, smaller than the crossover scale. So we can use 4-dimensional theory. And we use quasi-static approximations to look at the perturbations. So we have a Newton potential and gravitational potential, 3D curvature perturbations. And so this is the Parsons equations. And so now you notice that there is an additional contribution, which is coming from these fluctuations of the brain. So this is kind of the new degrees of freedom coming from 5-dimensional graviton. And this changes the relation between phi and psi. So in GR, and there's no additional contribution, so phi equals psi. So the post-Newton parameter is 1, but this phi is changing this relation. And this also gives the Higgs force. So this is the additional contributions to the Poisson equation sourced by density perturbations. And this scalar mode is coupled to density perturbations. So beta is just a function of time. And then it satisfies, again, the same kind of Poisson equation, but importantly with this nonlinear term. So for now, let's forget about this nonlinear term. And then you can have a linear system. So you can solve these equations to find the solution for phi and psi. And you notice that they are not the same. So and depending on the time, basically this is the behavior of phi and psi with respect to the scale factor. And if you have a modification of gravity at late times, these two potentials are not equal. And this basically excited people because we can test these deviations between these two potentials using large-scale structure observations, as Alessandra described yesterday. And in the future, we will get a very precise constraint on this kind of deviations. But of course, we have to go back to phi equals psi on small scales to recover the solar system constraint. Then we notice that, and the point is that we have this nonlinear term, and the important thing is that the coefficient is given by this crossover scale. And remember that to explain the accelerated expansion of the universe, this scale is huge. So this is the horizon scale today. Okay, so this is a huge number. So this is enhancing basically this nonlinear term. So this is the origin of this additional nonlinearity in the scalar sector compared with the nonlinearity in gravity. So because of this enhancement factor, scalar mode becomes nonlinear at much, much larger scales compared with the usual gravity. And the good thing about this type of screening mechanism is that it's a very simple quadratic equation, and you can easily solve these equations, at least for spherical symmetric case. But then you can easily already notice that once this nonlinear term becomes important, this is the squared of the nabla square phi. So now you take the solutions of this nonlinear term. Basically, nabla square phi is the square root of density variations. So for large density, because this is the square root of the density, this is suppressed compared with the usual GR term. So in this way, you can basically suppress the contribution from the scalar mode. And you can explicitly show this by deriving the solutions for spherical object, like the sun. And then this Einstein radius naturally appears. And this is determined by the combination of this parameter RC, which is the horizon scale today, and the Schwarzschild radius of the object. And as already Tony gave this number, so for the sun, so this gravitational radius is 3 kilometers. And this RC, which now we selected this scale as the horizon scale today, so it's 3000 megaparsec. So the Einstein radius for the sun becomes like 0.1 kiloparsec. So it's much, much larger than the size of the solar system. So above this length, you recover a linear solution, and indeed this is just a four-dimensional Brans-Dicke type gravity. So you have a difference between phi and psi. But inside this Einstein radius, because of the nonlinear interactions of the scalar field, the contribution from this scalar field gradient is suppressed. So you recover GR with small corrections, which is determined by this Einstein radius. And if you look at these correction terms, and this is written like this. So GM over R cubed is the spatial curvature of the object. And this is the curvature of the universe, because we basically chose our parameter to be the horizon scale. So basically, the screening is determined by the curvature of the object. And if the spatial curvature of the object is smaller than the curvature of the entire universe, which is very small, then you have a screening. So this is a very efficient way of suppressing the scalar field contributions below this Einstein radius. So this is the kind of screening mechanism we need to explain the solar system constraint. And we have a very similar Einstein mechanism in this DOS series. And for this, the same choice of the functions which we needed to explain dark energy. So that's the reason why I have this lambda 3 scale, which is determined by horizon scale today. We have the same Einstein radius. So we substitute the expression of lambda 3, and this becomes the same as this expression. So basically, it's the same Einstein radius in the DGP model. And we have a successful Einstein mechanism, at least inside matter source. M is the mass profile of the object. So let's just look at this term. So then you have phi equals psi. However, in this case, you notice that the Newton constant inside the Einstein radius is given by these functions. And these functions can depend on time. So there's a time dependence in the Newtonian potential. So this can be constrained by the lunar lensing observations because of this time dependence. But in addition to that, you got additional corrections if you consider the gravitational potential inside this matter profile, because this is the R derivative of this mass profile. So these parameters are determined by these two free functions endorsed. And especially this phi in this notation is a Newtonian potential. So depending on the mass profile, this changes your gravitational potential inside the distribution of matter. So this changes, for example, the structure of the star. But if you go to the outside, m is constant. So these terms disappear, and then you go back to GR. So Einstein mechanism works to restore GR, except for this time-dependent Newton constant, but it's broken inside the distribution of matter. And this was first found in the context of Beyond-Hordensky in this paper. So this can be used to set constraint on this parameter, especially this parameter, because this is the potential, Newtonian potential, which is a dominant contribution to determine the structure of the star. And we get a very interesting constraint, and the lower limit is indeed coming from the condition that you can form stable stars. And the upper limit is coming from some stellar observations derived by this paper by Jeremy Sakstein. So basically, for positive epsilon 1, stars are less compact, and the minimum mass for hydrogen burning star is larger than GR, and you can get some band from lightest red dwarfs. And this paper also shows that you can get some kind of upper limit, a very similar upper limit from white dwarfs. So using stellar structures, you can get constraint on these parameters. An additional constraint you can get is this Hall-Taylor parser constraint. As I said, this Newtonian constant inside Einstein radius is given by this function. But in fact, gravitational waves does not see this Newton constant. Instead, the gravitational waves are determined by this G function only. So there's a difference between gravitational constant for gravitational waves and the Newton constant. And this changes the prediction of orbital decay of the Hall-Taylor path. And so then you can get constraint on the difference between these two different Newton constant, and this gives a constraint on these functions. So finally, so this part is pretty much related to what Tony described. So these theories suffer from basically a strong coupling problem. So as I explained, the Einstein mechanism relies on nonlinear interactions. For example, for DGP model, that nonlinear equation can be derived from this kind of Lagrangian, where again, this suppression scale is determined by the combination of Planck scale and the Hubble scale today. But again, I emphasize that this scale is introduced because we use this as a dark energy model. Then put the number in this, we get that this lambda 3 is 10 to minus 22 gigaelectron volt, and this is 10 to 3 kilometer. And here comes a kind of coincidence that this is the kind of wave number we prove by LIGO. In this, the LIGO gravitational waves have very similar wave numbers. So that's basically the problem for LIGO observations. So one thing is that, as Tony explained, this is the cutoff of the theory because the quantum corrections like this kind of terms cannot be ignored if we consider energy scales larger than lambda 3. Even the LIGO gravitational waves, which has a very large wavelength, we are reaching this scale. So this means that the theory loses predictability and we need some kind of UV completion. But this also gives a large quantum effect, even for gravitational waves detected by LIGO. And this was studied by this paper. And they find that in this kind of theory, you can have interactions between gravitational waves and the scalar field perturbations given by this Lagrangian, with the suppression factor given by this lambda 3. So existence of this interaction means that the gravitational waves can decay into scalar field. And you can compute this decay rate, and this is determined by the wave momentum of the gravitational wave and suppressed by this lambda 3. But as I said, accidentally, the wave number, momentum of gravitational waves detected by LIGO is very close to lambda 3. So the decay rate is also a lambda 3, and which is like 10 to minus 3 seconds. But we detected gravitational waves from a merging neutron star, which takes like 10 to 16 seconds to reach us. So this means that these gravitational waves would have already decayed if we have these interactions. So basically, we have to remove this kind of interaction from the theory. And this gives this condition in the DOST theory. Remember that we had 2 remaining free functions, but one of the free function needs to be 0 to avoid having this kind of interactions. So we started from 3 free functions, one removed from the requirements that the speed of gravity is the same as speed of the light. And the other one is removed by this gravitational wave decay constraint. And we end up with 1 free function. And ironically, this is the same number of free function you had in the original Hordensky theory, but you have now a very different theory from Hordensky. So as you can see that the theory is pretty much squeezed by many fronts. So gravitational wave constraint. And I didn't mention about large scale structure constraint. But in fact, as I said, beyond the Einstein radius, you have a modified gravity. So even with current large scale structure data, you can constrain these theories. And then adding the gravitational wave decay, basically it's very difficult to for this theory to survive. This is basically the survived theory. So we are discussing about this part of the theory. So as I said, the only freedom left is 1 free function of G, but this part is now very different from Hordensky theory. But you can add usual K-essence kind of term and the cubic Hordensky term. And again, using this transformation argument, you can easily understand this new theory. Indeed, this is just a theory with usual K-essence and cubic Hordensky, plus some function of phi of G. So this is the usual minimally coupled gravity. Then you perform this conformal transformation depending on X, then you generate this theory. So this is the theory that avoid the inequality of the speed of gravity and speed of light, as well as the gravitational wave decay. But in fact, the gravitational wave can give yet another constraint on this Lagrangian. So if you look at the interactions of the gravitational wave and the scalar field, you now notice that there's another kind of interactions in this theory, mainly coming from this G3 function. And this, you can see that this is kind of the gradient term for the scalar field perturbations. So if you have some propagating gravitational waves, this can induce some gradient instabilities. And this puts some constraint on these functions in terms of EFT parameters introduced by Alessandra yesterday. So alpha B is determined by basically X dependence of this G3 function. And then this parameter needs to be constrained like larger than 10 to minus 2, sorry, maybe smaller than 10 to minus 2 to avoid this instability. So in this way, gravitational waves are giving a lot of strong constraint. And just to mention that, so how about the Einstein mechanism in this survived theory? And this was studied in these 2 papers. So I quickly mention that. So this is a survived theory. So we have 1, 2, 3 free function. I changed the G from G to F here. And then you can define parameters characterizing X dependence of this G3 and X dependence of F and other dependence using psi and zeta. And then you notice that in this case, even outside the source, in general, you have a difference between phi and psi. So you have to make this tuning between these parameters to satisfy the solar system constraint. But even doing so, you still find the difference between phi and psi inside the matter source. So this is an example. So this is the surface of the star. So you can tune parameters to get the agreement between phi and psi outside, but inside you still have a difference. So the Newton constant inside and outside is different. But again, also gravitational wave see a different Newton constant. In this case, again, gravitational waves is only sensitive to F. So again, you can put constraint from House theta parser, and so this beta parameter is constrained by this House theta parser constraint. So this is the Einstein mechanism in this survived theory. I just quickly mention about other constraint from gravitational waves. So one can get some constraint from gravitational wave propagations. So there are two modifications. One is the friction term, which is coming from this time dependence of gravitational wave Newton constant. And this changes the luminosity distance measured by gravitational waves compared with the luminosity distance you measure from electromagnetic waves. At the moment, the constraint on this is very weak, but in the future, we may get a better constraint. In addition, yeah, we already talked about the constraint on speed of gravity. In the scalar tensor theory, we do not have this mass term, but in the mass of gravity, for example, we have this modification of dispersion relation, and this is constraint. But if we consider dark energy theory, in fact, this energy is quite high compared with dark energy scale. So this doesn't give a strong constraint on mass of gravity as a dark energy model, for example. So finally, we are also interested in like generation of gravitational waves. And this is, I think, a point of discussions because beyond a very simplified situation, Einstein mechanism is not well understood. For cubic Galilean theories, it seems Einstein mechanism is highly effective, even for neutron stars. And also Einstein mechanism is working to suppress additional emission of scalar gravitational waves. In fact, there's an additional Einstein mechanism related to the period of the binaries. So you get a effective suppression of scalar gravitational waves. But as I said, anything beyond static weak gravity configurations, the dynamics of Einstein mechanism is not well understood. So this is an interesting open question. And if you have a breaking of Einstein in those theories, and then
yeah, sorry,
yeah.
5 minutes left.
Yeah, I only need a few minutes. So if you have a Einstein breaking inside matter source, then this changes the structure of neutron stars. And we looked at this in the context of beyond Foldensky, and also this is the case for the DOST in the survived. I think in the case with the equality between speed of light and speed of gravity, and you see that you can have a very strong effect on neutron stars. So this is another way of looking at the effect of breaking. In fact, and this is my final slide. So these are the discussion points about the Einstein mechanism, in addition to what Tony mentioned. So the main issue is this cutoff scale lambda 3. And the main issue was that accidentally, this cutoff scale in this kind of Einstein screening, Einstein mechanism, the momentum of the gravitational wave detected by LIGO is very close to lambda 3. But it pointed out by this paper that the theory may not be trustable even up to this scale, depending on the UV completion again. But then if you have a Lorentz invariant kind of completion, then you will get equality between speed of gravity and the speed of light. So then you don't need to worry about the constraint from LIGO. But of course, we lose predictability from LIGO. So then it's very important to have other gravitational wave observations like LISA, because LISA will prove gravitational waves with much lower momentum. So UV sensitivity is already discussed, but I would like to emphasize another point about the gravitational wave constraint. So this is IR dependence. In fact, I just talked about mainly the scalar tensor theory and put constraint from gravitational waves. But for example, DGP, brain world model, and the massive gravity, they have very similar kind of Einstein mechanisms for weak gravity quasi-static configurations. But they have a very different constraint because in this theory, for example, in DGP, below the crossover scale, you do not have any difference between the speed of gravity and the speed of light. And gravitational wave Newton constant is the same as the Newton constant you find inside the Bernstein radius. And there's no gravitational wave decay because the interaction between tensor and scalar is very different. So even if you have a very similar Bernstein mechanism, the constraint from gravitational wave observations are quite model dependent. So I stop my talk here, just showing the relevant length scale. So we introduced these large scale distance modifications. But then due to this very large length scale, we introduced this very large cutoff scale. Ideally, we want to trust classical theory above this length scale, but then we need to deal with nonlinear classical theory. And then, as I said, open question is, what is the strong gravity regime or dynamical system for screening? So this is still ongoing discussions. And then we have all this UV problem, as well as IR dependence on the constraint from gravitational waves. So I think I stop here.
So thank you very much, Kazuya. It was a super nice talk. And now questions. So we have a few minutes for questions before taking a break and then open the discussion session. So no question right now. Yes, one. Eugene, please go ahead.
Yeah, I'm just trying to find my button because I have too many monitors. Hi, Kazuya. Thanks. Very nice talk. So my question is this, right? So I mean, at least probably more a general question, but since you asked, like, so I'll open up the discussion. Is that so the speed of gravity seems to change depending on kind of like what the background situation is, what the background is. But we know that in E&M, when we have like light traveling at going through from medium to medium that have different refraction index, if you like, you're gonna see some sort of like light diffraction and even right reflection, if like remember Snell's law. So is there something that people can look for to test gravity by just looking for gravitational wave diffraction effects?
Yeah, that's an interesting question. For example, I talked about this possibility that we may have a difference between these two speed on cosmological scales, but then it goes back to the equality. But during this transition, yeah, there may be something interesting happening. And this is exactly the probably frequency we can prove by Lisa. So I think this is the claim of Claudia's paper. So maybe I shouldn't take the credit. But
okay.
So yeah, there may be something interesting when this transition happens, for example.
Okay, thanks.
Other questions? Okay, it seems not, but okay, so let's take 70 minutes of break, and we come back here at local time 4:40 for a discussion session that, and we would like to thank Claudia de Rham for moderating it. And please feel free to ask all the questions that you like to the speaker, to yesterday's speakers, if you have something to raise or something you would like to point out, or you disagree with the speakers, I don't know, whatever, let's have a lively discussion, and we'll come again in 17 minutes. So here we are. So welcome back, everybody. And let's start the discussion session. And let's thank Claudia for moderating the discussion. So Claudia, I know she doesn't need an introduction. She's professor in Imperial College in London, super well known for massive gravity, positivity bounds, and many other stuff. So Claudia, please go ahead.
Thank you very much, Marco. Thank you for this amazing conference. And also thank you to Tony and Kazuya. I was asked to moderate the discussion, but I think they've done an amazing summary in describing the current situation in for screening mechanisms. I had prepared a few slides just to set up the discussion. Let me share them now if I can. Yes, I'm allowed to. And but to be honest, they've done such an amazing job at just summarizing what's going on that I don't know if we need those slides. But let me just possibly catalyze a little bit the discussion in various directions. I've been thinking of four whiches. The first one, which model or screening mechanism we want to consider. And I think that's quite interesting that today's discussion's been focused on the Weinstein mechanism. I think a few years ago, there was much more attention in other types of screening mechanism. Maybe it's just a bias of the talks we had today, or maybe this is reflective of the current situation. I think that could be interesting to discuss. There's the which on, yes, a point related to that, which Kazuya made, which is a very interesting one, is even if we look at a particular Weinstein mechanism, the embedding of that model within the IR, as well as the UV, but within the IR, is going to be relevant, particularly when it comes to observations. And so the which observation, or which observational probes we're having has been extremely well summarized by Kazuya. This is not quite, and this is his slide, not quite the slide that summarizes all the observations, but I thought it was such a nice one that I decided to put it in, and maybe that will help us to moderate the discussion. There's also the which theoretical constraints we want to impose on ourselves, particularly when it comes to the screening mechanism, since, as Tony emphasized, they are really relying on type of models which are not standard, and so the theoretical constraints are typically very strong. I just summarized here a list of a few non-exhaustive potential constraints. Some of them are very tight with the observational constraints as well. So, for instance, the gradient instabilities may lead into decays, which are observable into observations. So they're tied to one another. And then these theoretical constraints, I put them as theoretical constraints within the screening models themselves, but they're of course tied with which UV embedding or which UV completion one wants to allow for ourselves when we're considering this type of models, particularly when we're dealing with the Weinstein, as was very nicely emphasized in Tony's talk. So in typical Wilsonian, local, and weakly coupled UV completion, the hopes for the Weinstein mechanism embedding are very, very limited. There's probably a dark future there. Should we even consider any alternative, or should we just give that up from the get-go? I think there was some nice discussion already at the end of Tony's talk there. Maybe this is a direction that can take more momentum. So I'll just summarize as the various level of discussion we may be able to have. I'm just here to moderate. So perhaps if we're spending a little bit too much time in one corner or another corner of this various interaction, I'll try to put it back into something relevant for everybody. But otherwise, it's really, the floor is yours. And I think that people can raise their hand if they have questions, or just start communicating their voices.
Maybe I can ask a question if nobody else. I mean, it's a question I actually wanted to ask at the end of the last talk, but maybe I'll ask it now. So, so you guys are saying that if we want to be in a regime in which higher, high energy corrections to Hordensky or to scalar tensor theories are under control. We need to be at low frequencies, and in that regime, you would expect the speed of gravity to be different than the speed of light, potentially. So there were, a few years ago, there was a paper trying to put constraints on the speed of gravitational waves using binary pulsars by, I think, Piazza and collaborators, and those are lower frequency than LIGO, because the period of those systems is of order hours or longer. So does that put further, is there a reason why that is not taken into account, or do you believe there might be other effects at play? Or more generally, do you think, we have data at lower frequencies from pulsar timing arrays and from binary pulsars. Can they be of any use to test these theories?
I don't know if Kazuya, you want to?
Yeah, I think so. What kind of frequencies are they?
Yeah, for instance, the relativistic double pulsar, I think we saw yesterday from Paolo's talk, is a period of 2.4 hours. I don't know in hertz how much that corresponds to, but for instance, nanograv pulsar timing arrays are targeting frequencies in the nanohertz band. They haven't seen anything so far. There is a tentative detection, but I wonder if what prospects you see if there is a detection, for instance, at nanohertz frequency. And of course, it's not like LISA, where you measure the delay between electromagnetic and gravitational waves directly, but still I wonder if indirectly you could put constraints on these theories, on screening.
Yeah, I think it's great to have any kind of constraint on the difference between the speed at intermediate frequency between LIGO and cosmology. So because we don't know when this transition happens, maybe Claudia had some estimations or something like that. But at the moment, if we have some constraint in between, this will put a very strong constraint.
I think the problem is that you don't, unlike LIGO, you don't measure this difference directly, you just measure the gravitational wave signal. But on the other hand, if you think about how gravitational waves are generated, C enters in the D'Alembertian. So I wonder if you can use the generation of gravitational waves to put constraints on this. And this was the idea behind, I think, this old paper I was trying to look it up during the coffee break. It was by Jimenez, Piazza, and Belton a few years ago.
Generation is a bit difficult again because of this Weinstein mechanism. So we expect to have very strong suppressions of any modifications for the generation. So propagation is good because it's propagating in a cosmological medium. So we see the modification usually.
Yeah, I think that relates a little bit to what Kazuya was saying, is that we don't quite understand how this Weinstein mechanism works as well as we would like to near within the setup of a binary pulsar, for instance. So the effect of that field in a region when the gravitational waves are generated in that region is not particularly well understood, to be fair, but that's typically not where you would expect a big departure to happen. When you have those models of dark energy that interact with gravity, it's because they are allowed to interact in an intergalactic medium, let's say, where you have very limited Weinstein mechanism, and that's where most of the effect comes in. But near the system, typically, you wouldn't expect it to have a very large effect on the gravitational waves themselves. Although, these are really, to be honest, open questions. I can't say, I don't think that's what you're asking, but from PTA, for instance, then if you could start having some constraints on the speed of gravitational waves at those scale, then that would bring you a big handle on any departure. As you said, you're not gonna, typically you don't expect there to see the signal with an optical counterpart, so you can compare, but you can even have some events which you track for a sufficient long period of time that you see a non-departure in the dispersion relation, and that could be a good handle on a good constraint on the speed at those frequencies.
I have a question about that. So we have a binary pulsar now called 1757 minus 1854 that is extremely accelerated near periastron, and much more than a Hall-Stellic pulsar, or much more than even the double pulsar. And the thing is, we looked into it and we thought it was marginally, it might be detectable with LISA, not at the basic frequency of that system, which is about 4 hours, 4.4 hours, but in one of the harmonics, because you get these sharp spikes in emission near the periastron. So if you could detect that system with LISA and you can see the gravitational waves arriving, at the same time as the electromagnetic signal, would that be an interesting constraint or not?
It is a continuous signal, right? So you can't use it to. Can you use it to determine?
I think yes, because you see the radio pulses from the.
Yeah, we see the radio pulses with extreme precision, so we can measure when the periastron happens with precision of a few microseconds. So we know that system extremely well, from the radio timing.
That will also help gravitational wave parameter estimation itself to see the pulses. I mean, but it would certainly, I think, put constraints on what they're after, CT minus C.
Yeah, if we have some kind of observations about this difference away from this cutoff scale, we can't now use the arguments that it's so close to the cutoff. So I think it's very important to have that kind of constraint from RISA bound.
Okay, thanks.
Could I ask a question about one of the other witches? Perhaps a very naive question. So in these screening mechanisms, one thing that I've always been confused by, and feel free to say that that's just too complicated, but is that a lot of the systems we study are in interesting environments. So I know, what we look at with EHT are supermassive black holes, but they're also at the centers of galaxies, at the centers of clusters. And so they're very biased places in the universe. And I'm not quite sure what mass to insert into these screening estimates. And a good example would be, the two EHT primary targets are the black hole at the center of M87, which is itself at the center of the Virgo supercluster. So that's a very massive object. And the black hole at the center of our galaxy, which is a much less massive object by comparison. And would a comparison of those two things ever be useful for this, or is the question naive, or is it just everything's so massive that it doesn't matter at that point?
Yeah, that's indeed interesting questions, because this screening happens because of nonlinear equations. So you have multiple sources. How screening happens becomes very complicated because you cannot just superpose these solutions. But of course, if you have very massive object and everything will be screened, but how the screening happens precisely depends on the configuration of the object. So this is another question, because we don't know very well what happens to the system with multiple sources with different configurations. We have some kind of simulations in a cosmological setup using n-body simulations. But in this case, in fact, we are not considering a very massive object. So it's kind of distribution of diffuse matters. So yeah, I think it's very complicated to solve nonlinear equations in the presence of multiple sources with no symmetry, for example. So that's another interesting things to look at. And nowadays there is a numerical code. I think Tony's group developed some finite element method to solve nonlinear scalar field equations. So I think there is some way to solve nonlinear equations, but to be honest, I think this hasn't been done yet.
Yeah, on that. So I mean, as you know, I mean, you've spoken to Daniela, and she did all the legwork on the numerical side of things. And even in that configuration, it was such a simple configuration that we were playing with, really, you know, it's at both at the theoretical level, I mean, and in terms of modeling the source, you know, so it really is really challenging to actually, because of the nonlinear nature of the field equation, is really challenging to sort of get anywhere with this. Just, I mean, I guess it's sort of question stroke comment really on that. I mean, is it likely that, you know, that thinking about things like these objects at the center of galaxies and whatnot, is that ever going to be competitive with the solar system constraints that we can impose for using Feinstein screening? I would say that's unlikely, right? Or you know, Earth Moon constraints and that kind of thing. Would you agree? It's just not going to be competitive.
Well, I think the one thing that we can get with non-solar system tests is something beyond one, right? I mean, we have one solar system, which is great, but inconvenient for comparison.
Yeah, but if you had a pulsar around Sagittarius star, for instance, that would be, which is a possibility, and maybe Paolo can elaborate on that. I think they would be very precise constraints. But I thought Avery was asking also about the different scales. The fact that, for instance, M87 star is the size of that black hole is 1 billion kilometers. And the black holes that we see with LIGO are 30 kilometers, 100 kilometers size. And those scales are right across the 1,000 kilometers that we saw was the cutoff scale. I mean, can that be, and the fact that the image measured by the EHT is in agreement with GR, LIGO data seem to be in agreement with GR. I understand that's, well, I guess that's generation. The answer will be that we're looking again not at the propagation of gravitational waves, but the generation. But those scales are right across the cutoff scale. So maybe wouldn't you expect something different even when it comes to generation of perturbations at those widely different scales? I don't know if the question is clear, but I was trying to formulate it as I went along.
Yeah, I mean, Kazuya probably has a better feel of it. But it's true that you go back to Tony's point, if you want to, typically, again, if you want to satisfy solar system tests, that typically means that the generation process at the level of the generation itself has to be very suppressed. Of course, you rely on using...
What I understood from Tony's talk is that when you go to the UV, the screening...
No, I meant from his point just now, in that the constraint from the solar system constraints are very strong. So if that means that we need to have a very strong suppression of the force within the solar system. And so in other astrophysical systems, if we have the same level of suppression, of course, it's another test, I agree, it's another one. But based on what we know in the solar system, if you export that to another astrophysical system, you expect the generation, the production of another scalar wave, for instance, or the effect on the production itself of gravitational waves to be very suppressed. I'm not saying that it's not worth having another system where we can see the suppression happening, but if we trust the suppression that happens in the solar system, then typically in other systems, even if the mass is quite different, typically the suppression is also very strong there, so that the effect on the production of gravitational waves or other type of waves is quite suppressed.
Is it not the case that you want, sorry, Is it not the case that you want small, if you want to find something interesting, you're generally going to want smaller objects rather than larger objects, just because the screening works, it works better for the heavier the object, right? Because you've got large, right?
You want less mass, but you want bigger distances. So when it comes to black hole,
yeah, basically it's determined by spatial curvature, right? So GM over R cubed. So we want to have a smaller curvature to be less screened. And unfortunately, all of these interesting generation of gravitational waves happens for a very large spatial curvature object. So naively, we expect that we have better screening. But having that said that, I mean, this is based on the intuition we get from a very simple weak gravity static solution. So maybe something radical happens if we include dynamics and go to strong gravity. A good thing is that if we are proving the scales, energy scales much lower than the cutoff scale, we basically need to solve classical nonlinear equations, right? So, well, depending on what Tony's point about the effect of UV compression to the classical theory, if we forget about that, we just need to solve classical nonlinear equations. So in principle, it's possible. But just technically, it's difficult.
Yeah, I mean, then you enter into how easy it is to solve those things about the well posedness of some of those models, and yeah. I agree with you. In principle, one can solve them classically if you want to trust them, but there's a reason why it hasn't been done so easily yet. Yeah.
I believe there will be talks on this later days, I think. So I saw the title about binaries and cubic Galileans and things like that.
But I agree with you. I mean, the very little analysis people do, we already see that the intuition we're trying to get from just the static, spherically symmetric, cubic Galilean, and that's the only intuition we really have. It doesn't work as well as we would have hoped otherwise in other systems. So. There's a few hands being raised. Maybe Connor, you had a question?
Yeah, hi. I was just wanting to ask regarding, you've just mentioned about particular signals which would be perfect to analyze, which would be really helpful. And Lisa's come up a few times now. I was just wondering if there was a particular system that Lisa will be able to observe that will be preferred in terms of placing constraints on these models that we've mentioned and gone through, or is it just the case that Lisa, anything that Lisa observes will be helpful? There's no preference to, say, supermassive black hole binaries or MREs, for example.
I think at the largest distance, if I understood correctly. I mean, you want an electromagnetic counterpart, and you want the distance to be as large as possible to maximize the constraint you get on the propagation speed difference, I think.
Yeah, I agree. So at the moment for LIGO, we only have this measurement from neutron star mergers at 40 megaparsec. So we want to extend this distance as well as the frequencies of gravitational waves. So we want to have gravitational waves which have lower frequencies. So that's the main thing we want to achieve.
Okay, great, thanks.
Jose, you'd like to ask a question?
Yeah, well, just to comment on this previous one, I think also eclipsing white dwarf binaries, I mean, they are very close, they are in our galaxy, but from the phase that is very well measured, you can constrain the speed. But my comment was, so you were mentioning before about screening and the generation of gravitational wave, and I just wanted to point out something which I think didn't came up in the discussion, which is that also like the gravitational waves, I mean, from the source to us, like, I mean, they will cross screen regions, and in these screen regions, you don't have the symmetries of the cosmological background, so you in general can have mixings between the tensor modes and other type of modes. And I think that's also an avenue which is interesting to further constrain these theories and understand better screening, which was not mentioned before.
Yeah, that's a very, very interesting point. Yeah. Andrew, you had a comment or a question?
Mine's on a different topic, so maybe Zakaria wants to go first.
I'm muted. Zakaria, maybe you want to go ahead then?
Hello?
Talking, you're muted.
Yeah. Do you hear me?
Yeah.
Yeah. So I have just a simple question. If we consider, for example, Hairy black holes, and we interpret the scalar field, the same scalar field as the cosmic scalar field, what will happen for the screening mechanism in the vicinity of this black hole, and what will be the case, for example, for those, because the Einstein mechanism will break inside the black hole?
Yeah, that's a great question. You know, if there's anyone in the audience that'd like to answer.
Yeah, there's this whole debate about no-hair theorems. For fifth symmetric theories, there's a no-hair theorem, so black holes cannot have any scalar hair. So I guess this applies to the theories we are considering. Then we don't expect to have any scalar hairs, but there's always exceptions, like you can have some time dependence in the scalar field, and then black holes can have a hair. So again, how this is related to the screening, that's another question, which is still not well answered, I think.
So can I follow up on this? So do black holes, I mean, is the geometry around black holes the same as in GR by virtue of the no-hair theorems or by virtue of screening? Do you expect?
My understanding is that if you assume static scalar field, it's the same as GR because of no-hair theorem, not the screening. But you can have some hairy black hole solutions if you have some time dependence. In that case, I think you can have some kind of Einstein screening for the scalar field so that the black hole looks like Schwarzschild should, but you have some differences.
And what about the case of primary hair when it's not still black hole and it's completely different from the black hole of GR? Because you are considering black holes with secondary hairs, and they have the background of Schwarzschild. But what about black holes who are different, who are like non-stealth black holes, and that we can detect them with non-dynamical tests?
I think this comes back to sort of Kazuya's point earlier about how difficult these things are to calculate. I don't know. I don't think. I mean, correct me if I'm wrong, but I guess nobody's probably can answer that question simply because it's just super difficult to actually do the calculation. At least even in the simplest theories that exhibit, like I don't know, like cubic Galilean or something. Yeah, you probably know better than me whether there's been any progress on that front, Kazuya, but I'm not aware of any.
Yeah, I mean, we are struggling to find any solutions beyond very simple weak gravity static solutions.
So, I mean, there's been a few papers on the effective field theory of black hole based on the symmetry around them. I don't know at all if that can be useful in trying to tackle that question in that framework. I don't know.
Well, we do have black hole solutions in those. Maybe Marco, you want to comment on. So there are solutions, but I'm not sure this is really a realistic black hole solution which exists in the universe. So that's another question, I think.
Yeah, there is. As Claudia was saying, there are, let's say, hairy solution, but it seems to turn out that most of them suffer from strong coupling issues, like was shown in a paper by Claudia and collaborators. So basically, the solution that we know that have this linear time dependence, and so they have a non-trivial scalar profile. Unfortunately, they turn out to be strongly coupled. So basically, the scalar field doesn't propagate on top of that background.
Excuse me, but there was a paper by Koyama about this problem of strong coupling by proposing a new method of scordatura and removing the degeneracy to generate and get to remove this problem.
Yeah, that's a possibility. Yeah, yeah, I've seen that paper in which he borrows the idea from the ghost condensate. And yes, if you basically modify a little bit the degeneracy condition, then in a controlled way, then you can get around the strong coupling issues and have every solution where the scalar field propagates. But I'm not sure how much this is related to screening. So to the original question, because we know that at least in the case of Bayesian screening, or I don't know, other kind of screening, the screening is given by matter. So instead in a black hole, you have a vacuum solution. So without matter, I'm not really sure how you can, of course, a black hole solution is a nonlinear solution. So like when you have screening that is given by nonlinear terms, even for a vacuum solution, nonlinearities are important. But then I don't really see how this is really connected to the suppression that you have, for instance, in the Bayesian screening that is given by the matter term.
And if we want just, without talking about screening, if you want just to connect the cosmic scalar field with hairy black holes, so is there any solutions of hairy black holes that can be relevant for late time cosmology? I know in Nordinsky there was a conjecture by Pedro claiming that there was no theory having hairy black hole solution that can lead to late time relevant time cosmology. But what about beyond Nordinsky and in those?
But to some extent, this time-dependent solution, this time dependence can be thought as some cosmological background. So, right, so in this sense, you can connect the scalar field to the cosmological scalar field. The problem is, at the moment, we don't have any physical solutions in this class. So that's probably the problem.
So I think Jose has a comment or a question.
I have a question, but for one of the other witches. So I don't know if Andrew maybe should go first.
Okay, so we only have a few more minutes left. I suggest Andrew goes, and then Jose, you can go.
Yeah, mine's on the completely other topic, which is Tony's topic, the UV completion. So just to add some comments. So I think I think it's probably true that, which is what Diwali's point was, is that Weinstein screen theories are completely different. They're not going to have a standard Wilsonian completion. And so it may be, although I wouldn't say it's all been proven yet, there's some examples, but it may be that those theories always violate the positivity bounds. Maybe there's a one-to-one between positivity bound violation and the Weinstein. But it is worth stressing that in the derivation of positivity bounds, you do put locality in that assumption. And it's, so the locality comes in basically leading to the Poisson bound, which determines the number of subtractions. And it's that overall growth that the assumed number of subtractions and dispersion relation that fixes the rules out the Galilean. If you had one more subtraction, it would be allowed. So that does suggest that if there is a way around for the Weinstein theories that is not standard, there'll be some degree of non-locality. And it's on that note, it's actually worth mentioning that 2D massive gravity, which although is mildly trivial, does have a UV completion. It's just corresponds to one of these TT bar deformations. So if you take 2D massive gravity and couple it to an integrable theory, the theory is still integrable. You can solve it, you can compute the S matrix. And what you find is the S matrix is actually, in that case, non-local. So it doesn't satisfy the polynomial boundedness assumption that goes into the derivation of the positivity bounds. And so there is no contradiction. And you also see that in that non-locality, it also exhibits a kind of Weinstein-like mechanism already in that exactly solvable situation. You can look at scattering of matter. So although in 2D there's no propagating gravitons, there are still static forces, as it were, because if you matter coupled to a 2D metric is still going to be modified relative to its Minkowski space. And you do see kind of non-local Weinstein mechanism going on there, but it is actually UV complete. You can actually solve things at the quantum level. So if you read any lesson from that, that is probably the route for the high dimensional theories as well. That's just my side comment.
Yeah, I mean, does anyone else has a comment in that corner of our witcher space?
I sort of agree with what Andrew said there. I don't disagree with any of those statements. I'd like to draw attention to the very last comment that you've put at the end of your fourth which is, should we really implement Weinstein within quantum gravity? I think that's a really interesting question, and I don't think I know the answer, but I think I sort of want perhaps my third to last slide maybe sort of suggested the regime where we should think about it. When you start to think about decay of a black hole, that's until it reaches the sort of point where it's a quantum black hole. This is where the question now really becomes, that's a very quantum gravity object. There seems to be, naively you would say there's a Weinstein radius associated with it, which is avoided strong coupling scale. It feels like something would have to give at least at that point. I do think there are puzzles actually, for example, in terms of, which I didn't mention, but when you think about sort of decay of a black hole and the rate at which it decays, and then decay of the corresponding classical configuration you would associate with the corresponding scalar, they're not necessarily the same rate. And that doesn't seem to feel right. Something seems to a mismatch there. So it feels like there's definitely something missing in our understanding of what's really going on. If as I think I agree with Andrew on this, that it's some sort of classicalization, UV completion going on. So yeah, I think there's definitely.
Yeah, I think we definitely can agree that there's a lot. that is certainly true. I mean, yeah, I definitely agree. There's a lot of elements one would need to be able to fully understand what's going on. We're very far from that. Yes, I think we only have a few more minutes left. So unless you have a very strong feeling about this direction, maybe Jose had a comment. We can end on that.
Yeah. So my question is, so normally when you said like observational constraints on a theory, like each observational constraint has some assumptions, and like depending on that, like people consider these constraints being more or less robust. So I was wondering, like for the theoretical constraints, what is the opinion of the panelists? If you will put like all the ones that are listed there like at the same level, or which one do you think are more robust, or what theoretical constraints do you consider that they are absolutely robust? Which one do you think that we could have more doubts, or just to get a sense of your opinion?
This is by no means meant to be exhaustive, right? So
yeah, well, whatever. Like from the theoretical constraints, what should be our guiding principles in your opinion?
Yeah, so maybe Tony and Kazuya.
I can go. I mean, okay. Should I pick one that I think is probably the most sort of powerful? The most important, I would say, ghost. If you've got a ghost in your theory, throw it away. I think, yeah. I mean, this is yeah. Let me just leave it at that. Of course, yes, you're right. You can treat it perturbatively, and I agree. I think this sort of alludes to there's a model we looked at where it appeared an effective theory. But then again, you had a UV completion, so that was really what we were trying to explore there. I mean, I think the point is that these instabilities associated with ghosts, they're extremely rapid. If you can imagine some scheme by which you can sort of cure them in the UV, then that's maybe something you could try to play with, but it seems something that's really quite difficult to sort of do away with.
I'm gonna let you talk, Kazuya, but yeah, I think I would like to agree with this in the sense, maybe if you really want to rely on your screening mechanism on a ghostly operator, you can't do that. And we often hear that, oh, that's just a problem about the quantum level, and classically that's okay. That is not true. A ghost is a problem. If you rely on it, is a problem at the classical level as well already, with infinitely fast instability. Okay, I've talked enough. Kazuya.
No, I agree. I mean, the ghosts are very bad. So, but also, I mean, gradient instability, this happens at the classical level. So the problem is that in order to know the fate of these instabilities, again, we need to know UV theories. So then it's a bit difficult to say whether this is really bad or not. But if we have a gradient instabilities, we cannot use perturbative computations. So this is really bad. So I think I would worry about that.
Okay, thank you very much. Perhaps we can thank Kazuya and Tony again for very nice discussions.
Yeah, thank you guys. And yeah, it was a nice discussion session. Thanks, Claudia, for moderating it, for taking care of it. And okay, and thanks everybody for participating, of course. And you can still ask questions to the speakers, to Claudia, if you like, on the Slack channel. So please write over there. And we can go on with the next speaker, David. Are you there, David?
Yes.
Oh, here we are. So, and let's move on. And it's a pleasure to introduce David Langlois. David is Director de Research of CNRS in France. He's based on at APC in Paris. He's an expert on many stuff. And today he's going to talk about black hole perturbations in modified gravity.
Okay, so let me try to share my screen. Is it okay?
Yes, we can see it.
Okay. Okay, so thank you, Marco. Thanks to the organizer for the invitation, and hello, everyone. So I'm going to talk about black hole perturbations in the context of modified gravity. So if it wants to move, sorry, I have some problem with my slides, that's okay. Okay, so as I guess you are all aware of, gravitational wave astronomy is an excellent opportunity to test general relativity in a strong field regime. And there is one phase which is interesting, especially interesting for modified gravity, because it is relatively simple, which is a ring down phase of a black hole merger. And the reason it's simple is because it can be understood with a linear perturbation of black holes. So what I'm going to discuss in this talk is what one can say about perturbation, linear perturbation, in the framework of scalar tensor theories. So I'm going to discuss modified gravity models in the context of scalar tensor theories. And I'm going to use the most general framework to date, which is the framework of dust theories, which was introduced already by Kazuya in the previous talk. So in the last years, there has been a number of works on the question of the perturbation of black holes in dust theories. So here is a list of papers. And the focus of my talk will be more on the quasi-normal modes. So the ideas which are obviously directly related to perturbations. So I'm going to discuss the traditional approach to quasi-normal modes, which is valid in GR, which is based on a Schrödinger-like equation. And then I will discuss an alternative approach, which we have tried to develop in some very recent papers with Karim Nui and our student Hugo Roussy. So they appear very recently on arXiv. So first, let me start with a kind of quick introduction to DOST theories. So Kazuya already introduced them, so I'm going to be rather short. So the idea of DOST theories, so DOST means degenerate higher order scalar tensor theories, is to can be seen as an extension of the traditional theories. In the traditional theories, you have a Lagrangian which depends on a scalar field and only on the first derivative of the scalar field. So in this extension, you allow now to have second derivative of the scalar field in the Lagrangian. And the DOST framework, the DOST theories, correspond to the most general family of scalar tensor theories, where you have a single scalar degree of freedom. And in fact, it includes most of the known scalar tensor theories. It's a bit like Russian dolls. So it includes, of course, the traditional scalar tensor theories. It also includes the Hordensky theories, which were discussed yesterday and today. And then it includes the beyond Hordensky theories. And finally, there is the family of DOST theories. So let me show the action for this DOST theories. So here I'm going to restrict myself to quadratic DOST theories, exactly as Kazuya did. So quadratic in the sense that they are quadratic in second derivative of the scalar field. So here in my formula, you see that the second derivative of the scalar field are the phi mu nu. So the action is up to this quadratic order in terms of this phi mu nu. So what you have, is, so you have a K-sense type term first, then you have a kind of a term which is box of phi, and then you have the Ricci tensor, which is multiplied by a function of x. So x is the kinetic term for the scalar field, and of phi. And finally, you have 5 Lagrangians. So this 5 Lagrangian has essentially all the combination that you can make in terms of second derivative of the scalar field and of the first derivative. So it's just combinatorics. And then you can multiply by functions in front, 5 functions in front of these 5 Lagrangians. So what is crucial is if you want to have only one scalar degree of freedom in the system, you need to impose some conditions on the function f, its derivative with respect to x, and the phi function a. And these constraints are called the degeneracy conditions. Okay, and they were shown by Kazuya. So here I'm not going to show them, but they were shown by Kazuya. So then you can extend this DOST series to cubic order, but I'm not going to discuss this today. I would like to emphasize that the constraint that Kazuya discussed on this series are not going to apply here, because I'm not going to assume that this model accounts for dark energy. So here I'm considering DOST theories simply as modified gravity models, and I'm not assuming that they explain the dark energy. So in this sense, all the constraints, the very stringent constraint that Kazuya discussed, do not apply in my case. And then finally, just for simplicity, I'm going to start in the models in the solution, the black hole solution I'm going to discuss. I'm going to start from Hordensky, which is a subcase of DOST theories. But as you are going to show up, even if you start from Hordensky, the DOST theory can show up quite naturally. And the reason is the following. The reason is that there is a kind of natural transformation when you have a Lagrangian, a family of Lagrangians. You can always do some field redefinition. So if you have a scalar tensor theory, you have a metric, you have a scalar field, So there is a kind of natural way to do some field redefinitions, which is to combine the metric with the scalar field and the gradient of the scalar field. So it means if you start from a metric G mu nu, you can combine this G mu nu with to add the product of the gradient of phi, and you get a new metric like this here. So it means in particular, if you start with an action, which is written in terms of this G tilde mu nu, and then you substitute for G tilde mu nu this expression in terms of C and D, then you will get a new action in terms of the metric G now. So these transformations are called the disformal transformations. And in some sense, they give you a kind of mapping inside your family of Lagrangians, inside dust. So what I want to stress is if you start with Hordensky theories, you have a framework which is incomplete, in the sense that if you start from a Hordensky theory, you apply this field redefinition, a disformal transformation, you end up with a theory which is no longer Hordensky. By contrast, in some sense, the dust framework is a complete framework, because if you start from a if you start from a dust theory, then you are going to end up with a dust theory. Another point which I want to stress is, of course, if there is no, if you consider only gravity, you see that two theories which are disformally related are equivalent. But as soon as you add standard fields, any type of field, assuming that these fields are minimally coupled to the metric, either G mu nu or G tilde mu nu, then you get two theories which are physically inequivalent. So let's move now to the black hole solutions in this type of theories. And so there have been several attempts to try to find some explicit solutions in these theories. And it turns out that one can find a black hole solution with a non-trivial scalar field. So in some sense with some dust hair in this series. And so here I'm going to discuss only non-rotating solutions. Okay, so black hole solutions which are static and spherically symmetric. So the metric has this form here. Okay, so the function A will correspond to the G00 function. And then you have a profile for the scalar field. So what is interesting is, although the metric, the geometry is static, you can in fact include some linear time dependence for the scalar field in the case of shift symmetric theories. And the reason is the following. The reason is, if you have a shift symmetric theory, everything depends on the derivative of the scalar field, the gradients or second derivatives. So this means that as soon as you take the gradients, you see that the time dependence disappears, which means that you can have a static spacetime. So with this kind of ansatz for the metric and the scalar field, then you can plug this ansatz in the equation of motion, the background equation of motion from the dust theory, and you can find some solutions. So one solution which is interesting is you can recover exactly the same solution as in GR, so the Schwarzschild solution, but at the same time you have a non-trivial scalar field. So in some sense, it's a disguised Schwarzschild solution, because there is a scalar field which is present, but you don't see it. You don't see it explicitly in the metric. So with this type of function, so this is a function f which is in front of the Ricci scalar in the Lagrangian, you can get this type of stealth Schwarzschild solution. So here I'm going to focus on the case where alpha is non-zero, but you could have some extra terms here. And then I'm going also to discuss, as an example, a non-stealth solution, which I'm going to call the BCL solution after the authors, Babichev, Charmoussi, and Leibel. So this solution has this function A of R here. So you can see that it looks like a Reisser-Nordström metric, but there is a plus here and not a minus, okay? And R minus is positive. So it's not exactly a Reisser-Nordström metric, and there is only one horizon. And in this case, I'm going to assume that Q is 0. You have to assume that Q is 0. And this can be obtained from this kind of Lagrangian, so with this function here. X is a constant in the first case. X depends on R in the second case. So let's discuss now the black hole perturbations. Okay, so I'm starting from a static and spherical symmetric metric. So when you have a static solution, a background solution, you can obviously do a Fourier transform in time, which I'm going to do. So instead of working with a time-dependent function, I'm going to work with omega-dependent functions. And then so this is very standard in general relativity. Then you can do a decomposition because of the spherical symmetry. You can do a decomposition in spherical harmonics. And usually you can distinguish between two types of modes, the axial modes or odd parity modes, and the polar or the even parity modes, which have a different dependence when you do a parity transformation. So they behave differently in a parity transformation. And then, so for example, for the axial modes, you see that it depends only on two functions, H0 and H1, if I go in a specific gauge, and this is a traditional gauge, which is called the Regge-Wheeler gauge here I'm using. In the same way, for the polar modes, you can fix a gauge, and then you have 4 metric functions which describe the metric perturbations. So in GR, this is all you have. But of course, when you are in a scalar tensor theory, you have to add the perturbation of the scalar field, and the perturbation of the scalar field appears only in the polar modes. It is 0 for the axial modes. Okay, so I'm going to work with these perturbations. So let me briefly recall what happens in the context of GR. So in the context of GR, and I'm going to discuss axial modes. So in the context of GR, the Einstein equation, the linearized Einstein equation, give in fact only 2 independent equations, which you can write as a two-dimensional system with this vector here, y, which is made of the 2 metric perturbations. And what is very nice is that you can rewrite this system of 2 first-order equation into a single second-order equation, which has a Schrödinger form, and which is given by this expression here. So here I've made, as usual, I've made a change of coordinates, and R star here is the tortoise coordinate. So later, I'm going to use an R star, which is not necessarily a tortoise coordinate, but here this is the usual Schwarzschild tortoise coordinate. And you have some potential, which is plotted here on the right. So then what happens is you can look at the behavior of the modes of the modes asymptotically. So asymptotically means near the horizon, and near the horizon here means when R star tends to -infinity, or at special infinity, and this is when R star goes to +infinity. And in this case, as you can see on the plot, you see that the potential goes to 0, which means you have a very simple equation of motion. And you have 2 types of mode, one mode which is outgoing, and one mode which is ingoing. So then if you want to define the quasi-normal modes, their definition is the following. you impose that there is no ingoing mode from infinity, from spatial infinity, and you impose that there is no outgoing mode from the horizon. So it means that you have to impose these two conditions on the coefficients here and here, at the horizon and at spatial infinity. And if you impose this boundary condition for the wave, for the perturbation, you find that there is only a discrete set of omegas which are allowed, and these are the quasi-normal frequencies. And what is specific, and this is the reason why they are called quasi-normal, is that there is an imaginary part in these omegas, which is negative and which correspond to a damping time of the modes. So now let me move to the axial modes in those theories. So for axial modes, the story is relatively easy in the sense that the equations have a similar structure. So it's a two-dimensional system with some functions here which depend only on the background solution and on the function in the Lagrangian of the dust theory. And this two-dimensional system can be rewritten in this form just by doing a change of functions. So I'm just doing a transformation of the y vector, and I get this structure here. So there is one difference, and one important difference with GR is that in GR, this psi function here is zero, automatically zero. But in general, in the case of dot theories, you are going to find a non-zero psi. And if you have a non-zero psi, you see that it's not immediate to find a Schrödinger equation from this. You cannot simply combine the two first-order equations into a nice Schrödinger-like second-order equation. But there is a trick, a very simple trick, which is to use a time redefinition. So if you do a time redefinition, in fact, you are going to change the system, and you can get rid of these two diagonal terms here, which depend on psi. So at the end, you get something which is zero on the diagonal, and then you can combine your two first-order equations into a second-order equation for the first component of y hat, which is going to have this shape here. So here I'm not assuming anything about R star. So R star is a kind of free choice, which depends on my rescaling of the radial coordinate. So it depends on this function little n. And what I would like to stress is that the potential, so there is, as a consequence, there is a speed of propagation, which appears here, which can depend on the radial coordinates. And in fact, this C and V, the speed and the potential depend on the choice of my rescaling for the radial coordinate. So let's apply this to axial modes in stealth Schwarzschild here. So here you have a function, these four functions which appear in the matrix are given by this. I mean, they are not interesting in themselves, except that they depend on one parameter, zeta. And this parameter zeta is in some sense parameterized the difference with general relativity. So if zeta is zero, you recover exactly the equation of general relativity. There is another point which I want to emphasize. So there is another pole another singularity which seems to appear in the functions here. So you see you have a singularity in Rs, but you have also another singularity at this other radius, which I'm going to call Rg, and which is a kind of rescaling of the Schwarzschild radius. So of course, when zeta is zero, you get GR and the two radii coincide. But this is not the case in general. So then you have to choose, you have to make a choice for this radial coordinate R star. So one solution would be to be like in general relativity and to choose the usual tortoise coordinate, the usual Schwarzschild tortoise coordinates. So if you do this, you are going to get a propagation speed which is this one here, so which is different from 1. So of course, if zeta is 0, then you recover 1, like in GR. Okay. But so you can decide to make another choice, which is to impose that the propagation speed is 1. So then it fixes the shape, the form of this R star, and this R star is given by this expression here, which in some sense is very familiar because it looks like the usual tortoise coordinates, except that the Schwarzschild radius, RS, is now RG, is replaced by RG, and there is a kind of global scaling. And what is even more surprising is that if you compute the potential with this choice for the radial coordinates, you get something which is almost like the usual Regge-Wheeler potential in general relativity, up to a rescaling here. So this looks very surprising, but it can be in fact understood by this formal transformation. So I told you that here I started from a Horndeski theory, but I can always do a disformal transformation and go to the frame where A1 is 0. And the frame where A1 is 0 corresponds to the frame where the kinetic structure of the gravitational waves of the tensor modes looks like GR. So it means that the velocity of gravitational waves is going to be a constant. So if you do this, so this is a disformal transformation here, you find you find the specific disformal transformation which is going to give you A1 is 0. So you have to impose this value for D over C. Then you get this metric. And of course, you are going to get some mixed term simply because the gradient of phi with respect to time is Q. And the gradient of phi with respect to R is some function. So you get a mixed term. But then you can absorb, you can redefine the coordinates. And in particular, you can absorb this mixed term by redefining the time. And it turns out that this is exactly the same redefinition of time I used before to get a Schrödinger equation. And then at the end, what you get is a metric which is exactly Schwarzschild up to some coordinate rescaling. But you see now that the horizon is RG and no longer RS. So this is very special, very peculiar. And somehow you start with a Schwarzschild metric with some horizon at RS. And then you go to another frame by a disformal transformation where the kinetic structure of the gravitational waves of the tensor mode is more natural, is more like GR. And then you discover that your initial metric get transformed into a new Schwarzschild metric, but with a different horizon. So this explains why you recover almost the Regge-Wheeler potential. So now I would like to discuss rather quickly another approach to this, an alternative approach, which is different from using a Schrödinger-like equation. And the idea is to use the asymptotic limit of the system. And as I'm going to show you a bit later, this is crucial to be able to solve the problem for polar modes. So the idea is the following. You start from your two-dimensional system, and let's consider that we look at the asymptotics at infinity. You do an expansion of your matrix M here near infinity. So it turns out that in general, there are a few exceptions, but in general, the solution will be, the asymptotic solution will be of this form, where epsilon is a diagonal matrix. So it's diagonal, and on the diagonal you have a polynomial of z, of the variable. Delta is a diagonal matrix with number, and f of z is just a matrix which is regular. So it goes to a constant when you go to infinity. And y0 contains just your integration constant. But what is interesting, and this is something we found in the mathematics literature, is that there is a well-defined algorithm to determine explicitly these diagonal matrices epsilon and delta, and which is rather recent. I mean, so I'm not going to explain the algorithm, which is a bit technical. So you can find all the details in our first paper or in this paper, but this is even more technical. But the basic idea is to diagonalize order by order the matrix M by using transformation of the functions of the Y vector. So it means if you start from Y, you redefine, you introduce a Y tilde with some matrix P. And so the new system is going to be in terms of this matrix M tilde, and the transformation M tilde is given in terms of M by this very simple transformation. So what is crucial is that P is going to depend on Z. So let me apply this now to the second example I showed you at the beginning. So I'm going to discuss the axial modes of the BCL black hole with this method.
Sorry, David, just 5 minutes left.
Yes, I know. So I have to, maybe a bit more, no? Okay, I'm going to.
Just to leave 5 minutes for questions, but okay, go ahead.
Yes. So at special infinity, you can do this expansion, and then you can apply this algorithm, and at the end you get something which is purely diagonal. So once you have something purely diagonal, you can integrate immediately piece by piece, and you get this expression here. So here I'm using for R star, so you can see that this expression can be rewritten in terms of R star, where R star is the usual tortoise coordinates with this function here for the BCL black holes. You can do the same type of analysis near the horizon with an expansion of this type, and you are going to find what you expect, except that here you have a non-trivial, I mean, this is a constant, which is not 1 for the propagation speed. So then you can compute numerically the quasi-normal modes by taking an ansatz with the right boundary conditions. So here I'm taking an ansatz with the boundary condition which correspond to the right ingoing and outgoing mode for the horizon and for the spatial infinity. So I skip the technical details, but at the end you can compute the quasi-normal modes. So here we have computed the first 3 quasi-normal modes in the BCL black holes for axial modes. And this is, so the big dots correspond to the GR value here. And then you see as you change the value of psi, you are going to move in the complex plane for the quasi-normal modes. So let me discuss, or maybe I can, yes, let me discuss a bit. Let me go back. Maybe one, I want just to explain that. So here, the basic idea is we are using 2 functions which are regular. So here we are assuming that F1 and F2 are regular. So we can decompose them in terms of Chebyshev polynomials. And if we truncate at some order, we get an algebraic linear system. And then we solve for this matrix system to find the values of omega for which the system has a non-trivial solution. And this is how we can find numerically the quasi-normal modes. So let me move now in the couple of minutes left to the polar modes. So the polar modes are much more complicated in scalar tensor theory. And the reason is the following. So if you are in GR, if you start from the metric equation, the linearized metric equation, you get only 2 independent equations, which correspond to 1 degree of freedom of general relativity. So this is a second tensor mode, which is in the polar modes. But if you are in a scalar tensor theory, you are going to get 4 equations. And the reason is that you now have 2 degrees of freedom. So one corresponds to the usual gravitational wave, and the other one comes from the scalar degree of freedom. So this means in practice that if you are in GR, you have a 2-dimensional system, which you can always rewrite as in a Schrödinger form. as Zerelli did a long time ago in the context of general relativity. But in a DOS series, the system is now 4-dimensional. So there are some cases where you can find easily a Schrödinger-like system. So it's a kind of generalized Schrödinger-like system with, which is matricial. So you have, in some sense, you have a matrix of Schrödinger equations where the potential is a matrix. But there are some cases, and this is a case that we obtain for the BCL black hole, where we were unable to find a Schrödinger form for the system of equations. So we have to use the asymptotic approach. So this means that we have been using the same algorithm in a systematic way to expand the matrix M near the horizon, near spatial infinity. And by using this idea of diagonalizing the system, we could extract the modes, the independent modes at the boundaries. So at spatial infinity, for example, we get these asymptotic solutions. So in the first two lines, you can recognize something which looks like we had for the axial modes. So this corresponds in some sense to the two gravitational modes that we expect. And then we have two other modes, which are completely different behavior, which is a bit strange, and which correspond to the scalar modes here. And you can play the same game near the horizon to get this. And then we have computed numerically the quasi-normal modes, which correspond to the gravitational boundary condition. So let me conclude very briefly. So I've tried to show you a kind of analysis of linear perturbation in the context of DOS theories. So the main idea to remember is that for axial modes, the story is very simple. This is very similar to GR in the sense that the equation of motion is a 2-dimensional system, but there are some subtleties. So one subtlety is that the potential and the propagation speed can depend on the choice of the radial coordinates. And we saw that in some cases, you could have a situation where the gravitational modes see a different Schwarzschild metric, which corresponds to a frame where the kinetic structure looks like the usual one. So for polar modes, this is much more complicated because this is 4-dimensional. But the main idea is that we have, in some sense, a systematic approach to decouple the modes asymptotically. And in the future, we would like to explore other solutions and ultimately also rotating black holes. Thank you for your attention.
So thank you very much, David. It was very nice. And so now time for questions. So we have one. Please, Reggie, go ahead.
Hi, thank you for the very nice talk. I have two questions about these formal transformations. So first is does it preserve screening mechanism? Say you had a screening mechanism earlier in Horn-Deskytt theory, and then you performed this formal transformation. Will it preserve the screening mechanism? And second question is, when you perform this formal transformation back to Horn-Deskytt theory earlier, did you have any guarantee that the solution will still remain to be a black hole?
Yeah, it's a good question. Yes, so concerning the first question, in some sense here, I would say that this formal transformation is not a physical transformation. So in some sense, anything physical which you have in one frame will be conserved maybe in another form in another frame. You see, it's just a purely mathematical transformation. In the same sense that in traditional scalar tensor theory, you can use the Jordan frame or the Einstein frame. Okay, so you use the Jordan frame where the metric is minimally coupled, and you use the Einstein frame where the structure of the gravitational waves is simpler.
Yeah, of course.
In some sense, this formal transformation is just a way, another way to look at the same theory. So the physics is exactly the same, but the physics can look rather different in a naive interpretation. So, for example, this idea that you get a Schwarzschild metric, a different Schwarzschild metric when you change frame is a kind of not obvious, and you have to be careful to see this kind of effects. So concerning the second question, this is a very good question. Is it possible to, in some sense, to find new solutions by using this formal transformation? So there has been recently a series of papers where people have tried to use this formal transformation to generate new solutions. But there is a kind of no-go theorem which was found that if you start, for example, from a naked singularity, if you do this formal transformation, you are not going to find a nice black hole with an horizon, with a nice horizon. So then in this particular case I showed, you start from a Schwarzschild metric and you end up with a different Schwarzschild metric. But there is another recent result. If you start with a Kerr metric, and if you do this formal transformation, you will find something which looks like another black hole, an axisymmetric black hole, but it doesn't look like it is not a Kerr black hole. So in some sense, you can play with this formal transformation to
thanks,
to get different metrics.
Yeah, can I follow up about the first question? That's
sure.
Okay.
Sure.
Yeah. Well, when talking about screening, there are couplings to the matter field. So I wasn't sure whether these formal transformations are going to spoil that. So you have a chameleon mechanism. There's a mass term that's going to be defined by that coupling, but then you performed this formal transformation. So I'm not sure whether that's going to preserve this screening mechanism. I understand, of course, that it's a matrix, but
yes. So okay. So maybe I should have clarified one point, and this is what I tried to say in the last sentence in this slide. So if you consider only gravity, so what I said is correct. So if you consider only gravity, if you go from one frame to another frame, this is completely equivalent, okay? Because you are just looking at gravity. If now you include matter, then the story can be completely equivalent if you couple matter minimally in one frame, and if you couple matter, the same matter, non-minimally with a disformal coupling in the other frame. Okay, so then the two theories are completely equivalent physically, even for matter. But of course, if now you coupled the matter in the first frame to the first metric, and then you couple the same matter to the other metric in the other frame, then the two theories are completely different in this case. Okay, so it really depends if you are looking at gravity at the metric, or if you are looking at the matter as well. And if you are looking at the matter, you have to be careful about how you couple matter to the metric and to which metric. Okay.
Yeah, thank you very much. I'm good. Thanks.
So, any other question? So it seems no. But
yes.
yeah. It's okay. Sorry. Yeah, I missed your hand. So please, sorry. Go ahead.
Yeah. Thank you very much for the wonderful lecture. I have just a question about stealth solutions. What is the thing that will guarantee if we have a stealth solution and we do this formal transformation and we end up on a stealth solution, or it will generate a non-stealth solution?
Yes. So okay. So the example is the example of the Kerr solution, which I mentioned, which answer your question. So in this case of this, so you start. So there are two recent papers on this topic. So if you start from a Kerr solution, which is obviously a general relativity solution and you do a formal transformation, then you obtain, so yes, no, it's a bit more complicated. So in the sense that you get a solution, so you start with a stealth solution in the DOS theory, initial DOS theory, and then you do this formal transformation, and you get a new solution, a new metric, which doesn't look, which is not K. So in some sense, this is a new, it's not a stealth solution, because this is not a solution that you could find in general relativity. But so this is not a stealth solution, but this is a new solution, which is a solution of some dust theory. Okay, so it means you can generate a non-stealth solution from a stealth solution.
Okay, and the stealth solution is found, for example, in Hordensky. We can do it also in
Yes, so there are many, so there are several papers which give, so in Hordensky or DOS series, so you have a kind of a set of conditions on the functions which are in the Lagrangian. So you have to make an assumption about, for example, you have to make an assumption about this, let me find it. Yes, this value for x here. Okay. So essentially there are two choices. So one choice is to assume that x is constant with a minus q square, but you can also detune. So you can.
There is no phone this weekend. No movie tomorrow.
Sorry, I think there was some.
So another participant to the workshop. Yeah. So another possibility is to detune this value of x, which is different from minus q square. And in this case, you get a different set of conditions on the functions which are in your Lagrangian. Okay, so the basic idea is that you can find many types of stealth Schwarzschild solutions, and you have a restriction on the type of functions in the Lagrangians.
Okay, thank you very much.
So we have one last real question, and then we move on. So please, you can ask your question.
Yes, I just a naive question. So it is very interesting to see that there's a change in the actual modes when you consider stealth Schwarzschild solution. So there's a shift, like I don't remember, is it C or zeta, that constant shift? So my question is, what is the metric function, or no, what is the functions in the theory that controls this parameter? Zeta, yeah, zeta.
Yes, zeta. So your question is what function in the theory?
Yes.
So essentially this is related to the, so in this case, this is related to the A1.
Oh, okay, okay.
Because you see the alpha, zeta is non-zero when alpha is non-zero.
Yes.
Alpha is the value of the first derivative of fx. Sorry, is the first derivative of f. And if I go back to this slide, you see that in Hordensky theory, you see that A1 is related to fx.
Okay, so it is the non-minimal coupling between the f and r, between the.
So yes, no, in some sense, this is really the A1. So it comes from this Lagrangian here.
Oh, okay.
Because this Lagrangian here contains a kinetic term for the gravitation, for the tensor modes.
I
so
see.
As soon as you have this Lagrangian, you are going to change the structure of the kinetic terms with respect to the gradient terms. So here in R, you have the usual kinetic terms from general relativity and the gradient terms. Okay, so if you multiply by f, it's always okay. You always find the same structure. But if you add this L1 Lagrangian, you get an extra kinetic term, which is not compensated by a gradient term. And this is why, so this is the same phenomenon in cosmology. If you want to constrain the speed of a gravitational wave to be the speed of light, you have to eliminate this L1 term.
Ah, okay, okay,
So
okay.
this is the same story here, because in fact, this is an effect which is non-linear. So it's not only at the level of the perturbation of gravitational waves, but it's really in the non-linear structure of the theory.
So that is a very special case in this general theory, right?
Yes, so it means, but what is interesting is that in some sense you can, or maybe not always, but in many theories, even if you start with A1, which is different from 0, then you can use a disformal transformation to go to another frame, which is a frame where A1 is 0. In some sense, it would be equivalent in the context of the Brans-Dicke type scalar theories when you go from the Jordan frame to the Einstein frame, because you know that in the Einstein frame, the structure of the tensor mode is exactly the same as in GR. And so this is the same idea. In fact, you go to another frame where the gravitational structure is very simple. And so there are many theories where you start with A1 different from 0, but then you can just do a disformal transformation to find a frame where A1 is 0.
Okay, okay, I see. Thank you.
So thank you again, David, for your talk. It was very nice. And now we move on to the last speaker of the day. Jeremy, are you around?
Yeah, I'm here. You just want me to share my screen?
Yeah, so good
Okay,
morning,
great.
Jen.
Hi, how's it going? Share screen, there we go. Okay, I'm going to assume you can all see this.
Okay, so let me introduce you first. Okay, so it is a pleasure to have Jeremy here. Jeremy is now professor in the University of Hawaii. He's very well known for his work on modified gravity, screening mechanism, and recently black hole archaeology. So you can start presenting your work, and thanks for joining.
Okay, great. Thank you, Marco. So hello, everyone. Greetings from Honolulu. As Marco said, it's actually about 6 a.m. here right now. So for me, it's good morning. And let me start by just thanking the organizers for giving me the opportunity to be here today and to tell you about my recent work. And what I'd like to tell you about is this project Black Hole Archaeology, which I've been involved with for about a year or so now, which I'm really excited about. And I'll tell you all about the details. So to motivate what black hole archaeology is, and why I think it's really interesting and fun and important to work on right now, I just kind of want to take a step back and ask the question, well, why are we all here today? The key word being today. So why are we having this workshop now, not 5 years ago, not 5 years into the future? And the answer really is that we're living in the era of gravitational wave astronomy, and with the recent release of the LIGO Virgo 03 data or 803 observing run, we've now got this great data set. So gravitational wave events that originated from merging black holes or merging neutron stars. And I think now is a really great time for theorists like myself to start thinking about what can we learn with this data set? What can we learn about the laws of nature? What can we learn about the objects that inhabit the universe? And the reason for this, if you look in the right-hand corner, I'm just showing you the number of events as a function of time, separated by LIGO's observing runs. And as you can see, in the first 2 observing runs, we had about 10 events. This has shot up to about 50 in 03A. This is only the first half of the 3rd observing run. We're going to have another half released soon, hopefully. And then from there, the number of events is just going to increase. So I think now is a really great time to be having this workshop and thinking about what sort of interesting physics you can learn from these events. So what I'm showing you here in the main plots is all of the events that LIGO Virgo have detected so far. So each one of these dots, in particular these blue dots, corresponds to a black hole which has merged with another black hole, so that's these 2 blue dots here, and formed a heavier black hole. And if you look at the scale on the left-hand side, you'll see that the masses for these black holes, at least the progenitors, so the merging black holes, are all of a very similar mass. They're all in the range somewhere 5 to 80 solar masses or so. And of course, this is not a coincidence. This is because we think that a lot of black holes in the universe, or astrophysical black holes, would have formed from the direct collapses of very massive stars a very long time ago. And so we expect black hole masses in this range. So So these are what people refer to as astrophysical black holes, and given the mass range, given the physics involved, it is very likely that the majority of the black holes in this data set, the black holes which merged, originated from the collapse of very massive stars, which exhausted all of their nuclear fuel and collapsed under their self-gravity to form these black holes. So what I would like to do today is tell you about how we can use this data set to learn about the properties of these progenitor stars. And this is where the link with archaeology comes in, because archaeologists study ancient civilizations and ancient history by using remnants of these ancient civilizations. They use things like ruins that they uncover to make inferences, and using these remnants, they can learn information about, say, how these civilizations lived and how they lived their lives. So what I'd like to invite you all to do today is join me in becoming black hole archaeologists, where instead of looking at the remnants of ancient civilizations, I would like to use the remnants of ancient stars which collapsed a long time ago. These are the black holes that we observe, and try and make inferences about how the stars that form these black holes live their lives, the processes that govern their evolution. And this is a really fascinating topic with a lot of different applications in areas like stellar astronomy, like nuclear physics. But I myself am a cosmologist, so I'm particularly interested in testing theories of new physics using this approach. So in particular, theories of dark matter and theories of dark energy. So this is what I'm going to focus on today. But there's a whole research field in this, trying to understand different stellar processes as well. And it's really fascinating. I wish I had the time to tell you about it. So the reason I want to do this is that if you do have this type of new physics, say dark energy or dark matter, they actually can change how stars work. And just to give you two examples of this, let's suppose that you think that dark energy is a theory of modified gravity with a screening mechanism, which is what this session is devoted to. Then if you have, say, a star in an unscreened galaxy, this modification of gravity will change the structure and evolution of this star. And that's because if you stop and think about what stars are, they're big balls of gas that would like to collapse under their own gravitational pressure and form a black hole. Sorry, their own gravitational, their self-gravity. But this is not what happens, of course. What happens is nuclear processes start fusing in the core. You produce this outward pressure gradient, and this outward pressure gradient balances the force of gravity, and you reach some stable equilibrium. This means that if you change the force of gravity, you're going to change the amount of pressure you need to support this star. And so you're going to change its structure and evolution. So maybe we can use these black hole remnants to look for signals of modified gravity or dark energy on the structure and evolution of these stars and do it that way. If instead that you're interested in dark matter or beyond the standard model particle physics, so say you're interested in very new light particles or dark matter coupled to the standard model, then these particles can be produced in the cores of stars. And because they're very light, they can free stream out of these stars without interacting again. And this means they act as a new source of loss. They steal energy from the star and escape into space. So this means if you have particles like axions or hidden photons, this energy loss is going to change the structure and evolution of the star, because the star is going to have to compensate for it somehow. And I'm going to go into a bit more detail on this slightly later on. But for now, I want to just take a step back and look at the sort of data that we have and try and understand how we can use it to do black hole archaeology. So what I'm showing here is just the first 10 events from the LIGO Virgo 01 and 02 runs, and that's just because this plot's just a little less busy. There's less going on, so it's easier for me to show you what's happening. And the same way that archaeologists might look for certain features in their ruins and try and understand what they were for. So maybe you've got some statue and you can try and figure out who the statue was of. It makes sense for us to look for features in this distribution and try and understand how they arose and the processes governing them. So if you stare at this plot, what you will see is there are kind of two gaps in the spectrum here. So the first one is referred to as the lower mass gap. This is a gap here between neutron stars and black holes. So neutron stars can't get arbitrarily heavy. They can only reach about 2.5 solar masses or so. Similarly, black holes can't be arbitrarily light. The lightest one you can form from direct stellar collapse is about 5 solar masses or so. And so we predict this lower black hole, this lower mass gap here. I'm not going to talk about this in my talk today. I just wanted to point it out just to be complete. But if you stare a little bit closer, and this one's a little harder to see, you can see there's also an upper mass gap here, and this is what I do want to talk to you about today. And the way you can see this is if you look at these blue points here, which are the merging black holes. Every black hole which merges, so just to remind you, these final black holes here, the ones the arrows point to, those didn't form from the direct collapse of stars. Those formed from these mergers. So every black hole that formed from the direct collapse of a star seems to lie below this dashed white line here at around 50 solar masses. So this is referred to as the upper mass gap. I'm just going to refer to it as the black hole mass gap today. And this itself is also predicted from stellar structure theory. And not only is it predicted, there's actually strong evidence for it in the LIGO-Virgo data now, even from the first 2 observing runs. So I would like to use these features to perform black hole archaeology and try and understand the stellar processes leading to them. So let me just tell you how this mass gap arises in stellar structure theory. So if you plot the distribution of black holes as a function of initial mass. So on the left here, I'm plotting various masses, and the red points are the black holes. On the bottom, I'm plotting the initial mass of the star. This is actually a plot I made myself using a stellar structure code called MESA. You'll see the distribution's kind of a bit strange. It's not what you might have expected at first glance, because you see there's a turnover. If you start with heavier initial stars, at some point you end up forming lighter black holes. Now, this is not what you would naively expect, because you would expect, well, this star is just a big ball of gas, runs out of fuel, collapses under its own self-gravity. Why isn't the final black hole mass equal to the mass of the star that I started with? Mass should be conserved. So this is due to various stellar processes, of course. So the first one is just stellar winds. So if I can draw your attention to this green curve, all I'm plotting here is y equals x. This is the line m in black hole equals m initial. So this is what you would expect to see in the black hole distribution. But in fact, because you have stellar winds, which removes some mass from the star, you actually end up on this white line here. So this is a very well understood stellar process. HD here starts for helium depletion, and that's because stellar winds are usually inefficient by the time you've reached the end of helium burning. So this is the line you would expect to see, but you've still got this turnover and this kind of decrease in black hole mass as a function of initial mass. And this requires a bit more explanation. And the mechanism driving this, or the underlying phenomenon, is known as the pair instability. So let me explain the pair instability to you. What I'm showing you here is the life cycle of very massive stars. So on the left, I'm plotting their central temperature, and on the bottom, I'm plotting their central density. And they start their lives off over here at helium ignition. I've chopped off the main sequence phase. And as they evolve, they get denser and they get hotter. So they move up towards the right here. Eventually, somewhere up here, you expect them to run out of fuel, and they collapse to form a black hole. And now that's at least what happens for this 40 solar mass black hole, which I'm showing you in the green track. But as you can see, the 70 solar mass black hole and the 120 solar mass black hole do some strange things. The 70 solar mass black hole loops around and ends up off over here eventually. And the blue 120 solar mass black hole doesn't even make it. It loops back on itself and stops. So what's going on here? What's driving this? Well, you've probably noticed this dashed white region here that I've labeled as unstable. In this region here, the star is hot enough and dense enough to pair produce electron-positron pairs from the vacuum. And when this happens, so you have 2 photons converting to two electron-positron pairs. When this happens, the electron-positron pairs are produced with very low kinetic energies because it's essentially just at threshold. And for this reason, they actually act to destabilize the star. And that's because being non-relativistic, they don't really contribute a lot to the pressure, but they do contribute a lot to the density. So they kind of act like dead weight and try and suck the star in without doing much to push it out. So as soon as these electron-positron pairs are created, the star begins to contract because it's now unstable. So usually you'd say, well, so what? If I take a star and compress it, this raises the temperature and the density. Typically, this is just going to increase the outward pressure and stop the contraction. And that is usually what happens. But in this case, because of the pair instability, when you contract the star, you actually produce more electron-positron pairs, which makes the star contract further. So this is an unstable runaway situation. So let me just show you what the end result of this is. So this is a very busy plot, which shows the effects of the pair instability. So it'd be great if you could follow along with my cursor. So if we start off here with evolved helium cores, As soon as we hit the instability, we produce these electron-positron pairs, and the star starts to collapse. Now, this collapse halted because, of course, there are heavy elements in the center of the star, and in particular, oxygen can be ignited explosively when the temperature reaches threshold. So the results of this oxygen explosion, and this really is an explosion, depends on how heavy the star is. So if you're not a very, very heavy star, you're just a very heavy star, which is, say, 50 solar masses or so, this oxygen will cause a series of pulsations. And this is known as a pulsational pair instability supernova. And during these pulsations, the star is pulsing so violently, it sheds off a load of mass, and it ends up becoming much lighter than it originally was. So this process can continue several times, but eventually, because it hasn't shed all of its mass, the star will exhaust all of its nuclear fuel and collapse and form a black hole down here. So it goes like that. If, on the other hand, the star is very, very massive, say 90 solar masses or so, in this case, the explosion is so violent that the entire star becomes unbound. Every single layer of the star is ejected, and there's no compact remnant left behind. So this is referred to as a pair instability supernova, and this is the origin of the black hole mass gap. The star just destroys itself. There's no black hole that's formed. If you're extremely heavy, so 200 solar masses or so, the pair instability can be quenched because some of the contraction energy goes into photo-disintegrating heavy elements, and the black holes are expected to reappear. I won't talk about these objects too much during this talk because where the minimum mass for this occurring is around 120 solar masses or so. So this is the kind of where the black holes start reappearing. And this is slightly outside the range of LIGO's current reach. So LIGO is not expected to see any of these upper edge black holes. So the black holes should appear at some point, and that's why this is a gap and not just a cutoff. Okay, so now we can go back to this diagram and understand what's happening. So what's taking you from this white line to this red line is the PPISN, the pulsational pair instability supernova. Because of the very large amounts of mass loss, you can end up forming black holes which are far lighter than their progenitor stars, and in fact, heavier stars can form lighter black holes than lighter initial stars. This falls to zero at the onset of the pair instability supernova, because at this point the star's ripped itself apart. There's nothing to collapse, and if you were to carry on, this would just be zero until a black hole started to reappear. So now we can define rigorously the lower edge of the black hole mass gap. It's this blue dashed line here, so it corresponds to the heaviest star you can form as a result of the competition between core collapse and the pulsational pair instability supernova. And if you just predict this in the standard model using stellar structure theory, you end up somewhere around 48 solar masses. So now I want to come back to my original question and ask how new physics can affect the location of the black hole mass gap, and just come back to the two sorts of physics that I wanted to talk about at the start of the talk. So as I told you, new light particles can affect the location of the black hole mass gap because they act as a new source of losses in the same way neutrinos act as losses in stars, and modified gravity could alter the structure of the star. So in order to figure out how these two different theories could affect the properties of stars, what I've done is I've implemented them into a stellar structure code called MESA and used that to make these predictions. So I'm going to start with new light particles. To understand how new light particles affect the location of the black hole mass gap, it's good to understand the physics of the pair instability a little bit more. And it turns out that the most important part of stellar evolution for the pair instability, at least as far as new light particles are concerned, is this phase here, the phase between helium ignition and carbon ignition. So during this phase, the star is fusing helium through the triple alpha process to form carbon, and that's how carbon's produced in the star. But there's also a secondary reaction which reprocesses some of this carbon into oxygen. So this is 12 carbon goes to oxygen 16. And this is really critical for the pulsations because this is the fuel. This is the fuel for the pair instability supernova. This is what gets ignited. So this reaction is crucial in determining whether the star pulses or whether it becomes whether it rips itself apart. So now you can understand what will happen if I add new light particles to this process. Because if I add new light particles, they're going to free stream out of the star, things like axions, and take away some energy. So if the star wants to compensate for this energy loss, it's going to have to burn at a faster rate to produce the same pressure gradient. This means it's going to spend less time burning helium because there's only a finite amount of it at fixed mass. It's going to run out faster. So therefore, we would expect the lifetime of the helium burning phase to be shorter if you have stronger couplings of the standard model to the dark sector. And this is what is borne out in our simulation. So what I'm showing you here is one example where I've taken axions and coupled them to electrons. So on the bottom, I'm plotting the axion-electron coupling. As you go towards the right, the coupling gets stronger, so the loss rate gets larger. And on the left, I'm plotting two panels. In the top, I'm essentially plotting the lifetime of helium burning. And I just picked a 63 solar mass star. And as you can see, the trend is glaringly obvious. The stronger the loss is, the shorter the lifetime of helium burning. And because the lifetime of helium burning is shorter, this means there's less time for this carbon to oxygen reaction to occur. And because there's less time for this, you end up with a higher ratio of carbon to oxygen by the time the pulsation starts. So this means there's less fuel for the pulsations just because you've not managed to create enough oxygen. In some sense, you've just reduced the amount of fuel available for the parents, for the PISN. And you can see that here in the bottom panel. And so if you run a grid of simulations to see what the effects of this are, what you would expect are completely borne out in our simulation. So here's axions coupled to photons this time. So again, I'm plotting black hole mass, this time as a function of the carbon-oxygen core mass. And larger values of this G10 correspond to stronger axion-photon couplings. The white curve is GR, or the standard model. Just as an example, if you look at the blue curve, you can see that whereas you can only form 47 solar mass black holes in GR, if you couple axions, you can get up to 52 or so. Different theories of dark matter will give you different distributions and different effects. So here I'm coupling dark photons to regular photons. Oh, sorry. And in this case, things go crazy. So if you look at larger values of epsilon, which is the kinetic mixing between the photon and the dark photon, you can see not only can you form black holes of order 70 solar masses or so, you can see in some cases the pulsations disappear completely and you get a very, very peaked distribution. And this is really interesting because it means that you can distinguish between different theories of dark matter using the shape of these distributions. And this is going to be important later on where I come to the archaeology aspects. Before I move on, I just want to talk about modified gravity because, of course, that's what a lot of you are interested in. So I performed a separate investigation into how modified gravity affects the location of the black hole mass gap. And this was a really great project. So it was actually led by a summer student, Maria Straight, who came to Hawaii to work with me for 10 weeks remotely, of course. What we had in mind was trying to test theories with different screening mechanisms. So by far the simplest proxy for this is just changing the value of G, and this would correspond to an unscreened star in an unscreened galaxy. So this lets us understand a lot of the interesting physics in a very model-independent way. And what we found is that if you increase the strength of gravity, which is this orange curve, you end up shifting the stellar towards the instability and making the instability worse. So now, as you would expect, this gives you stronger pulsations and more mass loss. Most screening mechanisms don't have weaker gravity, but you can kind of think of this as a proxy for beyond Horndeski theory. So we looked at decreasing the strength of gravity as well. In this case, if you have weaker gravity, so you lower G by 10% in an unscreened galaxy, you move away from the unstable region. You don't quite produce as many electron-positron pairs, so there's weaker pulsations and less mass loss. And this is borne out in our suite of simulations. So on the left, I'm just plotting the distribution again. Black hole mass is a function of core mass. So if I make gravity weaker, I can form far heavier black holes. If I make it stronger, then the heaviest black hole you can get up to is about 40 solar masses or so. And we were able to predict the location of both edges. So at this point, some of you may be thinking to yourselves, well, hang on, wait a second. Haven't I heard a lot about the black hole mass gap recently? Isn't there something that isn't this kind of at the back of my mind? And the answer is yes, because of course, in August last year, LIGO Virgo made this amazing announcement that in fact, one of the events in the O3 data set corresponded to black holes in the mass gap. So this made news all over the world and everyone was very excited about it. So the event's called Gravitational Wave 1905-21, and it is an event which emerged from two merging black holes, which very likely had masses inside the black hole mass gap. So the first one has 85 solar masses, The second one is about 65 solar masses or so. So as it stands, standard stellar structure theory cannot account for these two objects. So this means that either there's some sort of problem with stellar structure theory, something we don't understand, or these black holes formed through a mechanism which is not the direct collapse of astrophysical stars, so they're not astrophysical black holes. For example, it could be mergers of so second generation mergers, things like that. And there's a whole ton of explanations out there. It's just one event. But of course, I've just showed you that these kind of black holes could also be formed if new physics was at play. So as I said, this isn't the only possible explanation, but it's what we worked on. So we kind of joined forces, the modified gravity team and the particle team, and we just wanted to figure out, could this black hole or could this event have been due to physics beyond the standard model? And so we looked at various different explanations. We looked at new particles. We also looked at extra dimensions, which were pretty successful, and modified gravity theories. So if your theory is going to be able to account for both of these black holes, it has to at least make it to this gray region here, which is the overlap of the error bars between the two. And this was a really fun project to work on because I guess, like many of you, we kind of heard rumors about this event a couple of days before LIGO made the announcement. So we kind of decided to try and put the paper together and say something timely. We thought, oh, this is an amazing event. We really should say something. And it turns out we were very efficient at this because we weren't quite sure when LIGO were going to announce. So we picked a day and submitted it. And it turns out we actually submitted our paper to archive before the before LIGO Virgo team. So if you'd have checked archive that day, you would have seen this paper first and then the LIGO discovery paper, which was a lot of fun because we had a lot of fun on Twitter and Facebook chatting to the community about this and a bit of a laugh. My favorite comment was this one. So that was a lot of fun. And the reason I bring this event up is that I want to come back to it actually in about 5 minutes or so. Okay, so in the very, very last few minutes of my talk, I just want to tell you about how we can take these predictions that I've made. So these predictions, each one of these data points, I should say, takes about somewhere between 4 hours and several days to get out. So it's a lot of time invested in this. How are we going to take this and actually try and extract some physics from this? So we're going to do this using the black hole mass function. So very recently, we've been working on turning theory and prediction into analysis. And so what we've been working on is what we call an astrophysically motivated mass function. So the black hole mass function, of course, which is what we want to calculate and what we can extract from the LIGO Virgo data, is just the number of black holes NH with mass MBH. And the reason we want to introduce an astrophysically motivated one is that if you have a mass function whose parameters correspond to actual physics, things like the location of the mass gap, you can analyze the data to extract these parameters and draw meaningful conclusions about these different processes. So of course, we can't calculate this directly, but we can use the chain rule to expand it as the product of three terms. So the first one is just the initial mass function, which if you're an astronomer, you're very used to dealing with. If you're not, I'll just remind you that it's the number of stars born with mass m, ZAMS. So here ZAMS just stands for zero-age main sequence. Now, as I said, what's relevant for black hole formation is not really the main sequence, it's the helium burning phase. So you need to have a second function, which essentially takes the stars from being main sequence to helium burning. So this is a little less certain, this physics, but it's straightforward enough that you can parameterize it with a power law. And then this thing here, dm black hole by dmHb, this is the derivative of our theoretical predictions. So this is the derivative of this red curve that we can predict using stellar structure codes. So this is the really interesting part, the fact that we can make these predictions and calculate this thing here. So what we're going to try and do is try and use this curve here, or its derivative, to try and come up with a parametric form for this thing on the left, fit this thing to data, and then using that, we can extract some information about this distribution and hopefully be able to constrain some physics as well. So one thing I would just want you to note is that the derivative, so dm black hole by dm helium burning, actually goes to 0 at the peak. So you can see, because this final term is inverted, this 0 is going to lead to a formal divergence in the black hole mass function. And physically, what's happening is you have a lot of initial masses that give you the same final mass black hole. So for that reason, we expect kind of a big pile up at the location of the black hole mass gap in the mass function, and we've incorporated that into our mass function. So this is our proposal for for an astrophysically motivated mass function. And this is the product that I really want to sell to you today. So what I'd really like is for people who are interested in this thing to take this mass function, say, hey, maybe next time we analyze our data, maybe we should see what this does, or maybe we could extract some physics using this. So I've used the proportionality sign here because all of the physics that we aren't particularly interested in. I'm not going to talk about that. This is, of course, really interesting physics, things like second generation black holes, other mechanisms for forming black holes. But this is really the thing that I want to discuss. And we managed to find a parameterization which only has three parameters. And each of these parameters are physical in the sense that if you measure these parameters, you can learn something interesting about how stars work. So the first is this M black hole mass gap, which is the edge of the black hole mass gap. And as you can see, we actually get this formal divergence I told you about at precisely this location. So by measuring this position, you can look for the lower edge of the black hole mass gap. The parameter A, which I'll show you about in a couple of slides, describes how sharp this peak is, or how quickly you rise to this divergence. And as I'll show you, there's some actual interesting physics contained in there as well. And then B is kind of the combination of the initial mass function, the transfer function as well. So we have three physical parameters. In order to do our data analysis, we had to extend this to 7 for a couple of reasons. So first of all, solar mass stars don't form solar mass black holes. So you have to have some parameters which describe the lightest black hole you can form, and that needs to be put in by hand. Secondly, there might be black holes in your data set which are second generation. They might have merged from previous black holes formed in previous mergers, and it's important to account for these. And this is, again, a really fascinating, interesting area of astronomy, which has its whole own mass function dedicated to it. For us, we treat these as pollutants because we're really interested in understanding this, but we do include them in our analysis. For those of you who are interested in potentially using this mass function in your analysis, of course, you can take this part of the mass function and stick in your own favorite parameterization for second generation black holes, accreting black holes, things like that. And you should be able to get some interesting physics out of it. So let's see how this mass function works.
Jeremy, sorry, 5 minutes.
Yep, 5 minutes, perfect. Okay, so on the left-hand side, what I'm plotting again is this distribution, but this time I'm not adding any new physics. All I'm doing is I'm taking the standard model and I'm varying the rate of this important reaction, carbon to oxygen, within its experimental uncertainty. So of course, nuclear reaction rates are measured, they're not determined from first principles. And this leads to a very small shift in the mass gap, about 3 solar masses or so, and the distribution roughly is the same. So you see it doesn't change the shape of the distribution, it just shifts the location of the mass gap a little bit. On the right, I'm plotting the black hole mass function, which I showed you on the previous slide. So the solid lines are the black hole mass function you would get if you just use this formal equation up here and use these fits to the MESA data, whereas the dashed black lines are our actual parameterization. So this equation up here, and as you can see, they overlap beautifully. So you can actually use this to draw some inferences. And as you can see, if you do shift the location of the black hole mass gap, this divergence moves to different black holes. So if you try and fit this mass function to the data, you should be able to extract these the location of the mass gap. The parameter B doesn't change too much, and that's because it describes the initial mass function. That's pretty solid physics. And similarly, because the shape of this distribution doesn't change so much, the value of A is roughly comparable. So this is what you would do if you wanted to say try and constrain nuclear physics using this option. So not even new physics, just physics we know that exists. If instead you're interested in, say, new particles, this is where things get really interesting, at least for me, and really fun. So here I'm showing you the standard model prediction in blue and one of these hidden photon models in red. So these ones that basically don't have pulsations and are so sharply peaked. So again, the very large shift in the black hole mass gap is seen by a shift in the divergence point. But now you can see that the change in the peak, so how peaked this distribution is reflected in the parameter A. If you were to fit this to data, if the underlying data was the standard model, you get a value of A of order 0.39. For for dark matter, you get a value of 0.05. And this is what I mean when I say these parameters are physical. If you extract their value, you can actually learn something about the underlying physics governing the distribution. You're not just fitting functions to data. So this is why I'm very excited, and this is kind of the archaeology aspect. So of course, we applied this to the recent LIGO-Virgo data release, GWTC2. And what we found is that results are very sensitive to whether you include gravitational wave 190521 or not. And this makes a lot of sense because it may or may not be an astrophysical black hole. It may or may not be an outlier. We don't really know how this event formed. And because we've only got one of these events, we're not going to be able to learn how this event formed. I think the really interesting thing about 190521 is that since we've measured one event like this, hopefully we'll be able to measure more events like this. And then we can build up a population, characterize this population, include it in the mass function as an additional term if necessary, and understand the physics that led to its formation. So that's the really exciting thing for me. So since we don't know whether it's an outlier or not, we're just presenting results with it included and with it not. It's up to you to just draw conclusions about this. But on the left, I'm showing you what happens when you include 190521. On the right, I'm showing you what happens if you don't include it. So our work, or our mass function, is the orange fit, and as you can see, it kind of falls to 0 very sharply around where the location of the black hole mass gap. So this is where the divergence would be. It's smoothed out in the real data set, of course, because you don't have an infinite number of events. For comparison, I'm showing the LIGO-Virgo collaboration power law plus peak model. This is just a power law and a peak, and it picks up a pile up around 40-ish or so. Maybe this slide is a bit better for understanding the physics. So by fitting this to data, we were able to fit these parameters. So if you include 190521, we were able to make a robust detection of the black hole mass gap, and we got 74.8 plus or minus 4.3. Sorry, 4.3. This is just telling you that if you include gravitational wave 190521 in the astrophysical population, then of course you need you just have heavier black holes, so the location of the mass gap is going to shift up. And again, if you really believe this explanation, and you believe that gravitational 190521 formed from the collapse of a star, then you need some beyond the standard model physics, or some non-standard stellar structure at the very least. If instead you think 190521 is an outlier, or possibly not an astrophysical black hole, maybe we should remove it from the data analysis, then we find something that falls in line with the stellar structure theory prediction, which is 55 solar masses or so. Okay, so that's essentially the end of my talk. Just my summary is just me looking forward and telling you all the things that I'm really excited about, and why I think this is a really great time for theorists to start working on this and to think about this a little bit. So of course, we're expecting the O3b data release at some point in the near future. So we would like to redo the data analysis with that. And at that point, we're hoping there'll be enough events to maybe actually be able to constrain some models of particle physics, or some models of nuclear physics. Something which I didn't have time to tell you about, which I'm really excited about, is the possibility that that dark matter is heavy instead of light. Because if dark matter is heavy, instead of free streaming out of the star, it would remain in the core and contribute to the equation of states. And this means you could pair produce dark matter the same way you could pair produce electron positrons, and you would cause a new instability. And so we've predicted this instability analytically. It's tacked onto the end of one of our initial papers, but what we're working on now is actually implementing this instability into MESA to try and understand what the consequences of this are, and whether we can learn something about heavy dark matter models. For those of you interested in modified gravity, more work is really needed on this, so we need to be able to account for screening mechanisms, and I've got some ideas for how to do that, possibly time dependence as well. It's very exciting. It's a really, really fun and great topic to work on. So before I conclude, I would just like to give a shout out to my collaborators. It's been really great to work with these people. And this really is research which is greater than the sum of its parts, because we've got an amazing collaboration between particle physicists, between cosmologists, data analysts, people who are experts in gravitational wave observations, me, I guess. And this has produced some really great papers. So they're up there if you want to have a look at it. And I'll stop there. So thank you very much for your attention. And if you have any questions, my email address is up there, or my website. So thank you.
Cool. Thanks a lot, Jeremy. It was a great talk. And so I already see Chura's hand. I guess the first was Kiyu, and then Jose Maria.
Okay.
Yes, thank you for a very, very nice talk. So I have a question about the predictability of the modified gravity proposal. So if I, for example, if I remember correctly, what controls the screening is the distance of a galaxy from us, right? In general. And
that's not what controls the screening. So what controls the screening depends on your on the specific theory you're talking about. So if you have, say, the chameleon in mind, what it matters is not how far it is from us, but how far it is from is the local gravitational potential of this object of the galaxy. If for example you're talking about things like beyond Horndeski theories, then every galaxy is unscreened. Essentially, it's just the modifications is small.
Okay, I see. So, well, my original question was that if one day we can see some mass gap events again, which in some region where we expect there's no screen, then maybe this proposal can be ruled out in some sense, right? So this is what I mean by predictability.
Yeah, so this is if you want to look for rare events like 1905-21, then yeah, that's what you'd have to do. So I do have some ideas along those lines. For example, people are doing some very interesting work trying to statistically figure out where these things might have come from by cross-correlating with galaxy maps. But I think a better approach would be to go down this mass faction route. So I think, for example, let's suppose you had a theory of modified gravity with screening mechanisms. Now you essentially have two separate populations of astrophysical black holes, one which originated in screened galaxies, ones which originated in unscreened galaxies. And then maybe you can instead say, take two of these mass functions, stick them together, and when the LIGO data is good enough, try and pick out these two distributions. So I think this kind of archaeology approach is going to be more successful than trying to kind of sit around and wait for very rare events.
Okay, I see. Thank you.
Jose Maria?
Yes, well, thanks a lot for a very, very nice talk. I completely share your excitement about black hole archaeology. And just to connect to the previous talk of Kazuya, I think like having these sharp features in the mass distribution, also they can allow you to test like gravity at cosmological scales. For example, if you assume that the emission is not modified, but the propagation is modified, then you will change the inference. But now, since I also give talks about this, and I also have a theoretical physics background, and I used to get questions like some criticism about the robustness of the astrophysical model in the standard one. I want to share this criticism with you and to see what you think. So, namely, people usually complain about the fact that these predictions for the peri-instability supernova gap are made with 1D simulations, and that this might not be very robust. This is the first one. And then the second one, the fact that, for example, here in your analysis, you're assuming that the formation is the same across the history of the universe, but we know that metallicity changes with redshift. So this will also will impact your results inevitably. So if you can comment on this too.
Yeah, I can. So I have a backup slide prepared on this. So of course there are some uncertainty in the location of the black hole mass gap, and this has been thoroughly investigated. So for what we're doing, let me say two things about the uncertainties. One thing, I'm actually pretty excited about these because they can be characterized. So unlike other stellar environments, things like tip of the red giant branch, the effects on the black hole mass gap aren't overly large. I think the large. Well, let me just have this card. This line here corresponds to what happens if you take the uncertainty and this reaction rate from 20 years ago and go to 3 sigma. If you use the most recent experimental results, it shifts to 4. So the canonical different change in the location is about 4 solar masses or so. So with regards to 3D stellar modeling, it's probably not going to be feasible to use 3D stellar modeling to predict the location, at least not realistically. I mean, as I said, these simulations take about 3 to 5 days to complete. 3D simulations are going to take take months, so it's not possible to run grids. But actually, I think that what you said about metallicity is probably more important than 3D. So when you ignore 3D modeling, you ignore things like rotation, and you ignore things like mixing length and convection, and that's actually parameterized by this thing here, alpha MLT, which comes from mixing length theory. And this has only a tiny shift on the black hole mass gap. It's only about I think it's 1 solar mass or so. So I'm actually more concerned about Z, which corresponds to changes in environments and changes in over time. So you can think about Z as just black holes that formed in different environments, and so you expect it to give some scatter. So rather than say having some absolute value which shifts the black hole mass gap, I think changing the metallicity, really you should see it as, for example, giving scatter in the location. As long as you can fit a curve to that scatter, you can do what we've done. I think another really great thing is, in fact, in a completely separate project not related to the black hole mass gap, I've been working on getting Mesa to run very efficiently on supercomputers and on very large numbers of cores, and this has allow me to do MCMC with it for I think it might be the first time anyone's done it with Mesa. People have done MCMC with stellar structure codes before, but what's very exciting to me is that because this is a reasonably small shift and these uncertainties are kind of under control, we can predict them and characterize them. It means we can incorporate them into future data analyses, and hopefully include them in the MCMC, so we can kind of just include them in the error budget. As far as time dependence goes, one thing I'd actually like to do is to extend our model to include time dependence. So see if you can let these parameters either depend on time and extract them by splitting the LIGO data into different bins, different luminosity distance bins, or just assuming some time dependence and seeing what happens on the final distribution when you add it all together. That was a lot of talking. Did that answer your question?
Yeah, parts of it. I think yeah, I think there still are some uncertainties, but I mean, I think this is very exciting, and there's certainly a lot of work to do. So yeah.
Yeah, very, very. Yes.
Gregorio Carullo also has a right hand.
Yes, thanks, Jeremy. So hi. So my question was about the peak at 3035, which is not there in your model. So you think that it's just a different channel, or maybe there's some physical effect which
I can't explain this pile up. So maybe I can tell you the difference between these two models. So so the difference between our model and this model is that in our model, because the parameters are physically motivated, we essentially force the black hole mass gap to be at the location of this fall off, whereas this model it's just fitting a power law on a peak. So the location of the peak is allowed to float. It picks up a pile up at 30 solar masses. I'm not aware of any physical reason why we expect to pile up at 30 solar masses. I did think about it a bit, and I can't think of a good reason. That doesn't mean there isn't one, of course. It just means I'm not creative enough. But so it could be, for example, just the fact that you're letting this thing float, you're fitting a function to data. This is where the data wants your function to be. I don't necessarily know if you can draw physical conclusions from this, because of course you haven't started from a theoretical distribution and predicted this power law plus peak. You've just written it down and fitted it. So that's what the data tells you. I can't explain why the data wants a peak at 40 or so.
Yes, thanks. It answers the question. So of course there are
okay.
I think you might have muted yourself.
Gregorio, do you want to say something else?
Yeah, sorry, my connection I think was low. So I just wanted to say that, yeah, maybe regarding to the fact that the peak could be due to the fitting function. There are several groups which are also using non-parametric approaches to kind of fit the same mass function. I think one paper was already out from a group. So hopefully in the near future we will know if that's let's say robust enough to start to draw some physical conclusions, probably.
Yeah, I agree. Yeah, there are a ton of mass functions out there. So yeah, so as I said, I'm really trying to sell you this one as one which will give you some physics out there. But I think it's definitely interesting to ask say a complementary question, which is which function best fits the data. Maybe we can learn something that way as well. So yeah, it's actually pretty fun. There are a lot of different groups working on this because there's been a lot of fun discussions and a lot of interesting stuff to learn.
So it seems there are no more questions for Jeremy. So let me thank him again for his great talk. And I would like to thank all the speakers of the day again. They did an amazing job. And I hope you all enjoyed the day. And so let's meet again tomorrow for the third day of the workshops. And thanks for joining, and see you tomorrow.